Good evening, everyone. Today we'll be starting with the graph theory section of CSES problem sets. Okay. So first let's start with the basics, right? So generally, to represent a graph, we use a adjacency list. So it's actually just a vector of int. So what is this? Actually, it's an array of vectors. So let's take an example first. We have a graph such that 1 is connected to 2, 1 is connected to 3, and 1 is connected to 4. 2 is connected to 4, for example. So the list is going to store, the list of 1 is going to store 2, 3. List of 2 is going to store 1, 4. List of 3 is going to store 1. And the list of 4 is simply going to store 2. As there are no directed edges here, so this is going to be the basic adjacency list, right? Now, what we can do, basically there are like two traversal techniques, the depth first search and the breadth first search. So we'll be going through one of them. Like these are just basic traversal techniques. So we take a node, right? Like from that node, what we are going to do is we are going to go to all of its children in the list, adjacency list, right? And then if we have to see if it's not visited, right? So for that we have to take a visited array also, or a boolean, yeah, right? So if it is not visited, then we are going to again do DFS from it, right? And when we enter a node, we are going to make it visited. So this is just basic DFS traversal. So it does depth first search. Now let's try to dry run on this code. So basically what will happen, first we'll start with the parent node, let's say 1. It will mark it as visited, then it will go to its children 2 and 3, right? So let's assume it goes to 2 first, as it is first in the adjacency list. Then 2 is marked visited, then it will go to 3. 3 will see there are no children, so it will track back. 2, then it will again go to 4, and then it will track back to 2, and then back to 1. So this is like basic DFS traversal. Now, if we had to do like a basic question, like find the number of connected components. So what we do in that, initially we assign the number of connected components to 0. So we'll start from int node is equal to 1, and we go till all the nodes, right? Let's say n, node plus plus. So we'll initialize n and m. N is the number of nodes in our graph, and m is the number of edges in them, right? And what we're going to do, if it's not visited, we are going to make a DFS traversal through it and increase the number of connected components, and then basically return the answer. So this is like basic application of DFS. Now similarly, there is another BFS. What it's used for, like BFS is like breadth first search. So it will just calculate the distance of the child from the parent node. Yeah, like if you have to calculate, for example, distance of child from parent node, this is an application of BFS. So let's start void BFS. Here we use a queue for BFS traversal. What we do, we initialize a queue of int, for example, yeah. And in the queue first we push that node, and then we have to take a distance vector also to store the distance from the parent node. Yeah. So basically, first distance of u, let's say we pass the root here, right? Yeah. So distance of root is going to be 0 initially, and we are going to mark visit of root is equal to true. Now this is like basically putting the base case elements in the queue from which we have to do the BFS. Then the BFSs will do the BFS while our queue is not empty. Yeah. either that connected component is done or the BFS is complete. So first we are going to take the first element. How we do that in a queue, q dot front, and then we are going to pop it. Yeah, we don't need it anymore. Then we are going to go in for auto child in what? Adjacency list of that node, right? For each of the children, we are going to same as the BFS. If it's not visited, right, we are going to push the child back again in the queue, and we are going to mark the child as visited. And then after that, we are simply going to increment the distance. So yeah, that's it. So this is like the basics for the graph. Yeah. The most important things to keep in mind is, like, basically this part is before it has to enter the node, like before it has went to DFS children. This part is when it's going to the DFS of the children, and below it is going to be the part when it returns from the DFS to the children. Yeah, and this one is going to be when it has completed all DFS of the children. This is just like stuff which will help later. So this is like all regarding the basics of graph theory, like traversal techniques. So let's start. So yeah, the first question which is given to us is counting rooms. So here we are given a map of building, and your task is to count the number of its rooms. So the size of a map is n cross m squares, and each square is either a floor or a wall. You can walk left, right, up, down through the floor squares. So we are given input n and m. Yeah, we have to print the number of rooms. So so basically we just have to like count the number of connected components, right, which will give us the number of rooms. Okay, so let's start. Number of connected components will give us, okay, a size is a bit large, is the number of rooms. And let's do it using BFS. So initially we are given 1000 as the size. So let's take constant int mxn. We'll later be using vectors also. So 1a3 plus 1. This is initial to initialize the initial arrays. So we are actually given like characters, right? So we are going to take a character array. Let's take it adjacency list mxn of size mxn. This is for the adjacency list, or you can say int of int or vector of vector, whatever. And we'll also have a visited array for all of the nodes. And then we have what is the input n and m, and the count we have to calculate. So yeah, basically, yeah. So what we do, first we are going to take in n and m as input, the number of the height and width of the map, right? As we can see, it is one based indexed. So we are going to start, basically I is equal to 1 to n plus 1 rep j 1 to m plus 1 scene adjacency list of I comma j. So we have taken it one based indexing, like it's given in the question. Then what we do, we basically go through all of these again. What we see, if there are two conditions, if it's a dot, we'll do a DFS from it, for example, and see all the nodes we can visit it and mark them in a connected component. So either it should be a dot and it should not already been visited, right? So a adjacency list of I j equal to dot and visited of, so like it's not visited, right? So visited of I comma j. Yeah. And then what we'll do, we'll do a DFS with this as input, and then we'll do count plus plus. That's it. And then we'll return count. Now we have to write the DFS function. So like we did in the previous video, basically we are given two input like the x coordinate and the y coordinate. When we first start the traversal or on any node, we mark it as visited. We visited it, right? Okay. So then what we do, like that node can go in all four directions, right? Up, down, left, and right. So we'll have two arrays, int dx, and dy. So marking the x and y coordinates. So 0, 1, 0, minus 1. Yeah, right. So what we do for int, we'll just use the wrap here. Yeah. 0 to 4. We'll try to go all of the children. Here children are the left, right, up, down nodes. So we can just do it in one line also. If we'll make a function is valid. Is valid will check if we can go to that node or not. What we pass here, the x plus dx of y plus dy of I. Yeah. So then it will again do a DFS for these coordinates. So let's make a bool is valid function. We'll pass x and y. What it's going to see, I'll write in separate statements. So if x is less than 1, here it's 1 based indexing, right? Or x is greater than equal to n, or y is less than 1, or y is greater than equal to m. So we are simply going to return false. Not equal to, my bad. We're simply going to return false. So this is the boundary condition. We have to make sure that our traversal doesn't go outside the boundary. And we also have to see if it's already visited or not. If it's already visited, it's 1. Or it's a wall, right? So in that case also, we have to return a false. We can also merge these two conditions together. We'll do that later. So this is like the boundary condition, and this is going to be if it's feasible to go there, like it's not already visited, or it's a wall, it's blocked. Yeah, that's better. So this is basically, so let's try to submit it. Let's see if it gets submitted. Okay, I guess there was some issue. Let me see. Okay, it's giving runtime error. So I guess just a second. Yeah, I think we didn't have to return. We have to just print it. So hopefully it will get submitted this time. Okay, now let's move on to the next question. Labyrinth. So we are given a map of labyrinth, and your task is to find a path from start to the end, right? And we can walk left, right, up, down, right? So this is simple question, simple BFS DFS question. This question we could have also done using BFS. So what I'll do the second one using BFS. So what are we going to have here? Let's have an M, right? And what we are going to get, let's have indexes for the start index and the n index, right? Okay, so we'll take in n and m input, and then comma 0 comma n, right? So I guess, sorry, this is going to be n, my bad. So we'll do a double loop. Okay, we'll take in input, like we have to take in characters as an input. We'll take in one by one, not as a whole string. So we are taking each character as an input, so we can store the starting and end index, right? Now if it's like blocked, for example, we can just mark it as already visited instead of having to check another condition, right? So visited of ij is equal to true. So first create a visited vector of bool visited, right? And what we can do, like last time we did dx and dy, here what we are going to do, vector of pair int, just that we will create a pair instead, right? So we'll have -1, 0, 1, 0, 0, 1, 0, -1, right? That's it. We'll mark it as visited. Also, if it's like our starting index, it's a, right? Yeah, c is equal to a, that character. So we'll mark the sx is equal to I, the starting index, right, j. And similarly, if c is equal to b, the character we taken input is b, we'll mark the end index as I and ending index as j, like x coordinate and y coordinate. So basically we took input. Now we'll create a BFS function to solve, right? What will happen in the end of this BFS function? If we are able to visit, if we are not able to visit, right, the last node, so it's not reachable, then we have to simply print no, right? Cout no, and done, and return 0. So this is like basic. Else we have to print it. Else we have to cout yes. I think we also have to print the path. Yeah, we have to. So to store the path, let's have a vector. First, let's copy the is valid function from here. There's no need to write again if we can just copy it. So let's create a vector of vector, right, pair path. So this will help us in storing the path. And yeah, and here I don't think we need an adjacency list now. So I think, and also it's 0 based indexing here, so it's going to be greater than equal to n. Yeah. And if it's visited, we'll return false. Basically we have created our vector for path, visited vector, like vector of, yeah, so that's it. Now let's simply create our BFS function. So what we'll do here, we are going to we'll create a queue of pair of int comma int, as each coordinate is having both x and y coordinates, each node. So initially what we are going to push the starting index, we have declared them global, so no issue. Like now, like this is a base index, right, like already told in the start. Now while the queue is not empty, while the queue is not empty, what we are going to do, basically first we are going to take the node out. Like instead of taking the node out, so if we just take it, current x coordinate is equal to q dot front dot first, and initial y coordinate is equal to q dot back dot, no, sorry, q dot front dot second, and then we are going to pop that element as we already took its left and like first and second coordinate. So let's start now. Basically we have created a moves array, like a vector. We use this for range loop. We'll go through each of the coordinate, left, right, up and down. So this is just the same as BFS here, so there's no like difference here. we can use both, like in place of another. So like initial, like mv x coordinate is equal to mv dot first, mv y is equal to mv dot second. So these are like the move, like this -1 0 1 0, and then what we are going to check if is valid, like the next coordinates. What is the current index cx? We are going to add the like new coordinate mvx, and cy will add the another mvy. Now if it is valid, then we are going to first push it in the queue. I'll just copy it from here. Who is going to write it again? Okay, so that's it, and then we are going to mark it as visited, like we can also mark it as 1, like that's the same as. And then what we are going to store in the path of this coordinate, right? We are going to store the indexes, like what moves it took to reach here. That's why we created a global. 1 second. So like the path coordinate, see we are having a vector of pair of int comma int. So what is going to store each value? The block having x coordinate as this, y coordinate as this, is going to store a pair of int comma int, which are going to be the moves it took to reach here. mvx, mvy. That's it. So we are basically storing moves how we reached here, right? So our BFS is done now. Like BFS is done, basic BFS, right? And that's it. Now we have to track back, right? How we are going to track back? Let's create a vector of pair of int answer, and what is going to be the last index of this? It's going to be ex comma ey, right? Okay, my bad. This is just, we are creating a, we can also do auto, I think, I don't know properly. This is just a pair end which is going to show. Now this is a like basic, this is a technique we use in many places to just track back, like in binary lift, many places. So basically what we do, while n dot first is not equal to sx, or n dot second is not equal to ey, right? What we are going to do, in the answer we are going to push back the path of what? N dot first. I'll first write, then I'll explain, right? Then n dot second, right? So then we are going to decrease the value of each of these coordinates, minus equal to answer dot back and the first. N dot second is equal to minus equal to answer dot back dot second. Yeah. So what we did, initially we are at the end node ex and ey, whatever are its coordinates. Forget about the while condition. What we are going to do, initially we are going to store what are the coordinates it took to reach to this node, right? We are going to push back in the array, like in the vector, and then from these coordinates ex, like these two coordinates, like currently it's n dot first and n dot second, we are going to subtract both of them to get to the previous node. Basically first we are going to store the moves it took to reach that node, and then we are going to subtract that. We can, yeah. So what's then going to happen, n dot first and n dot second is going to get changed to the previous index. We'll keep on doing till like both of these, like one of these is true or not, like yeah, that. So basically, but here currently we are having the reverse path. So what we are going to do, just like reverse it, because currently we are from end, we want to have a path from, like there's exactly one path and we want it to have from where, like A to B. So we are just going to reverse the path. After reversing, what we have to do, I think we have to print the length. Yeah, generally first we have to print the length in these questions, then print the path. Yeah, now how we print the path, see, like the current move first, let's say, yeah, we don't need to even check that, huh? So simply we are going to go in the answer, all the moves for auto. Like we'll go through all the moves. What we are going to see, if C dot first, C is the character coordinate, is equal to 1 and that C dot second equal to 0, right? So what we are going down, right? Like the thing is, one second. So I coordinate. Currently the I coordinate here is in the y axis, not the x axis. So this is going to denote y, and going down is 1, going up is -1. So we are going to do C out D, right? Yeah. As we can see from this example, going left, like taking J as -1, yes. Like I are going to be rows and J are going to be columns. So it's a bit confusing when we'll start first, like Y and X are reversed here. So when we go from A to -1, 0, right, it is going to be left. Like we are storing here the opposite indexes. So yeah, like that. Okay, we are going to see out D, else if C dot first is equal to -1 and then C dot second equal to 0, right, we're going to see out U. Else if C dot first equal to 0 and C dot second equal to 1, right, we are going to see out R. Else if C dot first is equal to 0 and then C dot second equal to -1, we are going to see out L. I think first let's try to submit this much. If it doesn't work, we'll see the error. I'll go through again the syntax of this. Okay, so what we are doing here, like C dot first equal to 1, the first coordinate is going to store the J indexes, right? That's it. I hopefully, okay, it didn't get submitted. I'll see what's the issue here. Just a minute. Okay, so the issue is generally when we make a vector like global, right? So what we have to do to prevent runtime error in CSES, we have to just like resize them. Yeah, this is like a issue. Basically, we have to resize them to the current index to just prevent, you can say, the runtime error. So let's try to submit this again. Okay, just a minute. Yeah, currently we have just resized the like rows. We also have to resize the columns. Yes. So this is like basic problem in CSES. So we are going to go to each of the rows and then resize it to, let's say, m, like the number of this. Resize m. So let's see if it gets submitted now. Okay. Correct output, user output. We are also printing, right? User output, yes. Left up. Yeah, just a minute. So I think, yeah, so we're just having a semicolon here. Okay, so let's try to submit it again. Hopefully it will get submitted. Okay. So our answer array was getting shown as so here we put the wrong coordinate here. So that's it, I guess. Okay, so finally it gets submitted. So basic syntax error. So I'll go through this question once again. So what we first did, we stored the coordinates, starting and ending coordinates of start and end position. Then we did a BFS. BFS was just storing the moves, right? Like when we go from a particular index to another index, we are going to store the moves it takes to go from A to B, right? Till we reach the end node, right? But these moves are in the opposite direction. No, like when we go to the answer pair of int of answer, we are putting these nodes. We'll start from the end and then we put the directions in the opposite fashion. So we are just going to reverse it after, and then we are going to see out the size of it, right? And then we are going to print the basic coordinates DULR. If you have bit confusion, try dry coding it once. Okay, so let's go to the next question now. Building roads. Byteland has n cities and m roads between them. The goal is to construct new roads so that there is a route between any two cities. So our task is to find the number of roads required and also determine which roads should be built. So overall, what this question is trying to say, like there could be more than one connected component. So we have to just connect those. And we have to find the minimum number of required. So basically for every connected component, we take a node and we just connect them. Yeah, that's it. Basically we have to take n and m as input. So this is going to be very easy compared to the other. So let's take edges as global. So we took input. We are going to have a answer array. We are going to have a boolean vector of bool of visited and an adjacency list. Instead of list, we'll take a vector of vector here. See, it doesn't actually matter that much. Yeah. Okay. So then like in the last question as we did, I think we have to resize here also. So we don't again get a runtime error. Now what we are going to do, basically take an input for int m is the number of edges. So we have to take an input like x comma y. We have to take the input m number of times. So this is basic for loop to take an input. And in the adjacency list of x, we are going to push back y, and in the adjacency list of y, we are going to push back x. So that's it. Okay. So that's it, I guess. Yeah. Then what we are going to do, we are basically going to start DFS. Let's say in this case, as nodes are going to be from 1 to n I++. Basically what I'm going to say, like we did in the previous question, if it's not visited, right, we are going to increment the number of connected components. So let's take another global integer connected component plus plus, and then what we are going to push back in the answer, the current node through which we started that connected component, and then we are going to start the DFS. That's it. And yeah, that's it. We'll start the DFS. In the DFS, what we are going to do, we are going to mark this node as visited. We are going to mark this node as visited. After marking it as visited, we are going to go to the adjacency list of all the children in the adjacency list, and then we are again going to, if it's not visited, we are again going to go do a DFS traversal in it. Yeah. So after this we have our connected components. Now in the question it is given, you can print minimum number of the cities. Okay, so we are assuming we always have the answer. Now the answer will be CC minus 1. Like if there are two connected components, answer will be 1. So while like if CC is greater than 1, obviously what we are going to do, int a is equal to answer of 0. For int I is equal to what? 1. I is less than CC I plus plus. Like we have the first head of the first connected component. Initially we are going to take the another one and we are just going to print them basic and then swap. So okay, and B and L, and just keep on swapping them till we get CC. That's why we took it as global, so we can just simply do CC is greater than 1, or we can also have an inner condition if CC greater than 1 break or something like that. So let's start submitting this question. These are like very easy questions, I guess, like for basic BFS and DFS, I guess. Hopefully it will get submitted in the first. Okay, nice. Okay, let's start with another question. Message route. Now we are getting in the flow. So whatever this guy's name is, S network has N computers and M connection. Your task is to find out if you can send a message to M if it is possible. What is the minimum number of computers on such a route? So the first line has 2 integers, the number of computers, they're numbered 1 to n. Okay. So basically we have to find if we can go from 1 to n in a graph, and what is the minimum number of computers on such a route. And I guess there is at most one connection, and then we have to print k if it is possible to print k, and then the number of computers on a valid route. So basically what we have to do, we have to see if we can go from 1 to n, right, and also keep storing the parent nodes along with it to get the path. That's it. Yeah, so let's do it. I think mostly the syntax is going to be same as the previous question. Like let's take n and m as global, and in n and m. So I'll just write it comment. What we have to do basically, just use BFS to find the shortest distance, right, from what 1 to n, and store parent info along with it. That's it. That's what you have to do in this question. We'll have a vector of int of adjacency list. We'll have a vector of bool for visited. We can also have integer also, that doesn't actually matter. And then we are going to have a vector of int of parent. See, there is one important thing when we declare this is very important, like it will give TLE many times in CSES. When we declare a function like parent like as -1, so if it is global, this will make only the first element, this is very important, as -1, because you know n is not specified, no? Specified. So this is all the basic initialization we have to do. Now let's go to the main function, C in n, C in m. We are going to resize like we did in previous part. Later we are going to, instead of global, we are going to pass them one function, so we won't need to take care of this. And then we have to also resize n plus 1. Yeah. And basically for int I is equal to 0, I is less than equal to n, we are going to mark all the parents as -1. -1 is to show that either this is a root node or it's not currently visited. And then we are going to take an input of all the nodes, int I is equal to 0, x, y, will go to as many times as there are edges. Say in x, say in y. Adjacency list of x dot pushback y. Adjacency list of y dot pushback x. And then we'll have a BFS function, right? In the BFS function, what we'll modify the parent array, and in the end, if we'll see that parent of n equal to -1, right? So we can't reach this, so we have to print impossible, and we are going to return 0. Else, what we are going to do, we'll do when we reach here. So first let's write the BFS function. Okay. Like basically what you're going to start with here, we don't, like, everything is global now. So basically the root node is going to be 1 here. We are going to mark it as visited. We'll have a queue of int q, and we are going to push that node in it, and while queue is not empty. Like the procedure is going to be the same. First we mark it as visited, then we pass the root node into the queue. Root here, like, there could be more than one also. Like there will be a question later on for multi-source BFS where we'll be pushing that more than one. Base case, like, like 1, 2, 3, for example. Now then we do int u is equal to q dot front, just like small syntaxes, and basically like we always do, we take the front element, then we pop it while the queue is not empty, right? Now while the queue is not empty, we are again going to, okay, my bad, sorry. So we are going to now go to all the children in the adjacency list of u. Now if it's not visited, now if the children is not visited, we are first going to mark it as true, like we always do, and then we'll mark the parent of v is equal to u. We can also use DFS, it doesn't matter. Then we are going to push this node. So basically BFS is done. We have all the parents stored. Then what we are going to do, now BFS will return us the parent. Like last time in the labyrinth question, we used this while loop, right? Instead we can also use a stack. Like let's take an example, like the final node as n stack int of s, right? While z is not equal to -1, like we reach the first node. So simply we're going to push z in the stack, and z is equal to parent of z. Like this is just, I'm showing like different ways of doing the same thing. Then we are going to do the cout s dot size and l, and then while the s dot empty, while the stack is not empty, we are going to just print the top. So we don't need to reverse it, right? So like this just what it does is we don't have to perform the reverse operation. That's it. So like this is a very easy question. Like basically we are storing the parents with the help of BFS or DFS, and then we go back and just print them if we can reach it, of course. Hopefully it will get submitted in the first run. Okay, I think there is some problem. Okay, yes, there is some problem. Okay. So in just a minute. Yeah, I think so. Instead of reserve, there should be resize, I think. Yeah. So now let's try to submit this. Yes, also like we have to print a space in between them. So this gets submitted, right? Now let's go to the next question. Building teams. There are n pupils and m friendships between them. Your task is to divide the pupils into two teams in such a way that no two pupils in a team are friends. You can freely choose the size of the team. So basically what we have to say, like, if we can make a bipartite graph or not, like that's it. So like we just have to make a bipartite graph in this question. Bipartite graph is such that all connected nodes are of different color. So it's just a different wording we have to say. 10 raised power 5. Yeah. So with this question, we'll also get idea of bipartite graph. I started the recording now. Yeah. So let's start with this question now. Now we'll just remove that bullshit of resizing here, as we are getting like many resize ratio or whatever ratio that is. So we simply have to see if we can make a bipartite graph. Now we'll take constant int mxn 1e5 plus, let's say, 69. We'll just take 5, like int n m. We'll take a column of mxn. Color, this is just to store all the colors. Yeah. And we'll have a vector of int of adjacency list mxn. Vi is like defined as vector of int. We don't like we can use a visited array, but instead of visited we can have like one more color. Like let's assume we are trying to print or graph with color or graph with 1 and 2, right? We can assume 0 as an indicator if it has already been visited or not. Initially everything is 0 in this. It's a global array. So we'll, instead of a visited array, we don't need it, because we'll assume that if its color is 0, it's not visited. That's it. Okay, so okay, let's go. We are going to take an input n and m as we always do. I is equal to 0, a comma b. I is less than m, I plus plus, same a, b. And, like we can also write everything in one line. Okay, we can also write it like this, like in CP how we do it mostly. The shorter, the better. We'll have a boolean to return our answer if it can be colored, right? If it's false, basically, so what's going to tell? We are going to see out impossible and endl and just return it. If it's possible, then we are else, obviously it's going to print all of the 1 and 2, right? We'll color it using 1 and 2. So we just have to make a function boolean, which will, this is to check, but we have to see now there can be more than one connected component also. So what we are going to do, we are going to go all of the nodes, right? If we don't have a visited, if color of I is not equal to 0, right, that this is same as having visited of I, we'll make a DFS. DFS, what we have to pass? The current node. We have to pass the current node, the color, and the parent, right? So what is going to current node is going to I. Let's say the color of that connected component is going to be 1 and minus 1 obviously going to be parent. Return false. If this DFS is going to return us false, then we're simply going to return as false, as we can't form it for that connected component, so we don't need to check further. In the end, like if we check for all the connected components, for all of them it's returning true that we can form it, then this color function will return true. And now the DFS function, basically int node, int color, int parent. So basically first we are going to mark the color of that node as C. We don't now see if color is marked, then it's already visited, right? Then we are going to go all the children in the adjacency list of this node. what we are going to say, if child equal to parent, we are simply going to continue. But if it's not visited, aka color of this child is equal to 0, right? We are going to do something. Now, else, if it's already visited, means color of this child is equal to what? Color of this node, then we are going to return false. And if it somehow managed to survive through all of that, which means we are able to form a bipartite graph. And then what we are going to do the same procedure we did here, like recursion to see if it's returning false or not. If DFS of this current child node and color, how we change color? We do a XOR with 3. This will change 1 into 2 and 2 into 1, and then we pass the, what are we going to pass? The node, yes. So if it's going to return false, then we also return false. That's it. XORing with 3 will change 1 into 2. Color of child equal to 0, not already colored. Let's see if it gets submitted. Like, these are like very basic questions, basic graph theory questions. Hopefully it will get, where is 48? Return 0. So where was I? Hopefully it will get submitted. Now the real fun will start when we'll go to like other algorithms, Dijkstra, Bellman Ford, and okay, we are getting a wrong answer. Everything is empty, 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 empty. Just give me a minute, I'll see what's the issue. Okay, so the issue was the color function was not getting called. So why was not it getting called? Because we are taking scene M and M. Yeah. Okay, a very silly mistake on my end. So let's go to the next question, right? Byteland is having n cities and m roads between them. Your task is to design a round trip that begins in a city, goes through 2 or more cities, and finally returns to the starting city. Every intermediate city has to be distinct. So basically we have to like cycle detection, right? Like what is in like cycle detection in an undirected graph, aka if a node is visited and it's not a parent, it's a cycle. That's it. As simple as that. Okay, so basically we have to print number of cities. So like we'll just hard code it fast. Yeah, we'll just code it fast, not hard code. Okay, so let's start. We'll do as we did in the previous question. Constant int mxn is equal to 1e5 plus 1, right? And so we just have like starting index, right? Yes, we'll have a starting index and index. I'll talk about this later. So basically we are going to have a vector of int of adjacency list of size mxn and in a parent of mxn and a visited. So this is what? This is basically a cycle detection problem. Cycle detection problem in a undirected graph, right? If a node is visited and not a parent, it's a cycle. That's it. In undirected graph we don't have to do anything else. Now let's start. So int we take scene n and we are going to take an input for int I is equal to a comma b I less than m I plus plus scene a b adjacency list of a. We are going to push back b in it, and in the adjacency list of b we are going to push back a. Yeah, that's it. And what we are going to, like in the previous we had a answer storing, bool answer. So we can also directly do it. We'll just say if it's not valid, we'll just create a function for it. If it's not going to valid, we are going to see out what impossible, as we kept on doing till now, and then endl and return 0 if it's possible. Now what is this starting and ending index, SI and EI? This is like when we complete a cycle, the last two nodes, like the first node and the ending node, so which complete the cycle. So first we'll do that only. We'll have a vector of int of answer. Let's say x is equal to EI. Like cycle will start at SI, it will go up to EI, and the next node is again going to be SI. So we took x is equal to SI, right? We are going to answer dot push back EI. And while x is not equal to SI, we are simply going to like track back answer dot push back parent of x. Like parent of EI, like the previous element, will keep on doing till it's not equal to SI. And then we are simply going to push EI again to complete the cycle. Here we are assuming the cycle starts at EI and ends at EI. We can do both also, that doesn't matter actually that much. Like we can take SI first, yeah, and then we are going to see out the size and then all the like elements in it. For auto sin answer, see out what see answer. Now we just have to write the is valid function. This is just going to like just like the previous question, you know what it's going to do. We'll go through all the nodes. If it's not visited of I, we are going to say what the DFS is going to return. If it's going to return true, we have to just pass the node and parent. We are simply going to return true. That's it. And if we are not able to return true, we are going to return false. See, we can change the order, that doesn't matter. If we can return false internally, we can return true internally, that doesn't actually matter. So just main thing is the logic of the code. Now we'll write the DFS int node int parent. So as we always do, we are okay, caps lock case should be off. Visited of node is equal to 1, and then parent of this node is equal to what? Parent, right? And for all the children, auto child in the adjacency list of this node, we are going to first visit them. Okay, we have to check if the child is equal to parent, right? Then we are basically going to continue. Else if it's visited, okay, if this node is visited, what's the issue here? Okay, it's like okay, so let's take it as P. If it's visited, if it's a child and visited, we detected a cycle. If it's not visited, then we'll do a DFS. If DFS of this child and node is true, we are going to return true. Yeah, first we are passing the child, then the parent, that's it. And what we have to do, if it's visited, like we get our answer, we can store starting index as V child, like V is child, generally like basic node is U, so EI is equal to U. This is the node and this is the child, and then we are going to return true. I guess hopefully Generally it's denoted by V, and node is denoted by U. So like this is a basic question, cycle detection in an undirected graph. Easy peasy. Let's submit this. Hopefully it will get submitted in first go. Okay, again it gave runtime error. It's not printing anything. Let's see why. This time I'll debug without stopping the video. We took an input, right? AB, we push back. If it's not valid, we are going to see out impossible. Okay, so I don't think there is any issue in that. For I equal to 1, I is less than, if it's not visited, if DFS of I comma minus 1. We are returning true here, just we don't like to optimize a bit. Like if we get a cycle, we don't need to worry about. Now in the DFS, we first mark it as 1, parent of node equal to P, auto child in adjacency list of node, if child equal to P, continue, if it's visited, if the child is visited. You see, just like basic syntax error, I guess. Let's try to submit. Hopefully it will get submit. Okay, there's still runtime error in some questions. Why is that? Because we have to return false. Yes, if all the nodes are complete and we don't get a cycle, then we are going to return false. Okay, let's see if it gets submitted. And okay, it got submitted. Then this is monsters question. This is a question where, first of all, this is going to have a lot of implementation. This will clear the basics, and most probably I'll get many errors while trying to submit it. So this is a question on multi-source BFS. After this question gets completed, like basically BFS, DFS will be done. Then we'll go into the algorithms like Dijkstra, Bellman Ford, Floyd Warshall, etc. So let's start this question. If it gets submitted without any error, that's going to be very amazing. So we and monsters are in a labyrinth, like earlier we done. When taking a step to some direction in the labyrinth, each monster may simultaneously take one step as well. So our goal is to reach one of the boundary squares without ever sharing a square with the monster, right? So how we do this? This is a multi-source BFS question. First, we are going to take all the position of the monsters and imagine them as lava flowing, right? Like in each step, the monster can go up, left, down, right? So first, using all the monsters, we will do a BFS and mark all the times, minimum times it takes for them to reach that particular block. And then from the person, like which is you, we'll do another BFS. We'll see that if we are somehow able to reach the boundary such that we reach all the indexes, all the blocks, a time less than taken by the monsters. Yeah, so that's it. It's going to be a very good implementation question. So let's start. First I'll just write a bit of theory. Like we have to imagine monsters as lava flow, and we have to use multi-source BFS, right? Let's have B as capital to find the minimum time taken to reach each cell by the monster. Yeah, to reach each cell by the monster. So this is like basic, you can say the algorithm, what it's going to be. And then we will do BFS. from the starting position and find a path such that we reach the what? The nodes there before the monster arrives. If they exist, those paths. That's it. I think constant int. See if it gets submitted now without any error, like it's going to be amazing. So here let's try something different. We are going to have a struct point. Just a struct. Struct is just a self-defined data structure. Struct point, and we'll have the direction coordinates int dx of 4. Like let's take 0, 0, 1, minus 1. Int direction of y coordinates -1, 1, 0, 0. And then we'll start with the main function. Here I won't create any more functions. I'll just do everything in the main. Hopefully the errors are going to get reduced. Let me see the input, and I have my height and width of the map. So we are going to have dot star a, m, and m. So we are going to store the monsters and the starting index. That's it. Like last time we took characters, now here we'll take vector of strings as an input. L is standing for labyrinth. Video is getting recorded now. Yeah. So we'll take a string, vector of string. So basically for int I is equal to 0, I is less than n, I plus plus, string s, scene s, and L dot push back. We are going to push that string in it. Now we'll have the sx and sy for the starting position. And I guess we'll create a vector of int for time, right? Mxn, vector of int mxn. So basically we have made a vector of int of time, like because we have like x and y coordinates both now. So what is this? Is a vector of int. X coordinate are up to this index, y coordinate are up to this index, and they are all initialized by -1. This one is going to be for the monsters. So we'll have a queue first. Queue pair. What it's going to store? A point structure like the coordinates and int. Yeah. So like first just let us mark the we can also do this later. Yes. First we should take the input. Not the input, will store the indexes of the monsters and the starting index. So if labyrinth of I, j is equal to what? M, या फिर A. Sx is equal to I, Sy is equal to j. That's it. If L of I, j is equal to M, which means it's a monster. So we are going to push in the queue. Okay, that's why it's important to have this queue up. Yeah. Like instead of so what we are going to store? The coordinates of the monsters, and the initial time is 0, right? So we have to also include this in a pair. Like the struct is a pair, but the input in a queue is also pair, right? This is okay. Like actually it was good in the first place. So now we have already made all the base case monsters while the queue is not empty. What we are going to do, basically as we always do, q dot front, and then we are going to do q dot pop, right? After doing q dot front and q dot pop, we are going to take the int x is equal to current dot first, y is equal to current dot second, t is equal to, okay, my bad, it's going to be dot first dot y, dot first dot x, Yeah, so we are basically getting x and y coordinates of the monsters. Like one by one, we'll go through all the monsters. Instead of is valid function, we can write everything here also. Its one-way syntax is right. Less x is greater than, let's say, n minus 1. Or like that's it. Or what's the condition? If it's not a wall, right? Wall here is just, it's not a hash, I think. Or time of x, y is not equal to -1. This is like memoization condition as you do in DP. Because if it's not -1, it has already been visited, and it's a BFS, so it has already been visited by a lesser amount of time. Yeah, we'll continue. Okay, it's showing both are x. Okay, yeah, so see, like if time is already updated, we can't minimize it now because it's a BFS. Then what we are going to do, if like it's valid, right? The current node, we are going to mark it as T. Like we pop the node and we mark it as tree. Then we go to all the 4 directions from that node, right? What if, like, you understand now? Int nx is equal to what? X plus dx of I, and y is equal to y plus dy of I. Q dot push nx and y. So what we are doing here, either what we can do, either we can update this time condition right here, but then we have to again check this condition inside. So that's why we are just first what we are doing, pushing all the 4 nodes. If they are can be reached, then we are going to update the timer at those nodes. So basically this will give us the time taken by the monsters to reach. What we want in answer, a string, right? So let's have a string of answer first, and this will have a flag to say if we can reach or not. Bool flag is equal to false initially, and then we'll have a vector as we earlier had. Here we'll have time 2, same mxn vi, mxn -1, and we'll have we have to show the path also now. As in the earlier questions we did, we'll store a vector of int of path n plus 1, vector of int of m plus 1 comma 0. This is for the path. And then what we're going to have in the queue, this is going to be very interesting. What we can do, like last time we had a pair this time we are going to have a tuple, right? Tuple is just like triple index. See, that's why I told this question has like lot of implementation. Let's name it as Q2. What it's going to store? Index, time, and we also have to take care of the direction. And then we'll push what we are going to push, the x and y coordinates. And then what's going to do? Time. Initial time is going to 0 as we are starting from here, and direction is going to be 0. And why we are taking here a 0? Because like 0 will indicate 0 comma -1. 1 second. 0 can indicate that. Like 0 can indicate 0 comma -1, 1, 2 and 3. So basically we pushed in the, okay, while q2 dot emt, while q is not empty, we are basically what are like basic BFS, q2 dot front, q2 dot pop. See, if it gives the wrong answer, I don't even have, like I can't even debug it. It's a very large. So what we do for a tuple, we'll just create an auto ptd, which is equal to current. Like for a tuple, what else we can do? We can do it also like this. Point p is equal to get 0 of current. Like this is just basic syntax and stuff. Int t is equal to get 1 of current. D is int d is equal to get 2 of current. So yeah, that's it. Instead of these, we can just create auto. Like auto is really amazing, you know. And now we have to check. Like basic condition, boundary condition, it's less than 0. P dot x is greater than n minus 1 or greater than equal to 1. P dot y is less than 0. P dot y is greater than n minus 1. M minus 1, my bad. And what else condition is going to be? If it's a wall, what was it? P dot x, P dot y is equal to, okay, what's the error here? Okay, no error. Now what we have to say, a condition for failure here, if the time required, not the failure, if we already reach this block, right? Somehow we already reached this. I don't think that will happen. But if we have already came to this block again, we already storing the minimum time for it. I don't think this condition is going to be used, but I'm still writing. Now what are the conditions? The time it required to reach this time it required to reach the monster, right? Time it required by the monster to reach this block is less than equal to the time of, okay, so like this condition is the important, like in the time from the monsters, what we are saying, if that time is less than equal to t, right? But there is one more condition. What if it's minus 1? That monster can't even reach there somehow, like monster is blocked, like something. We have to make sure that time of y is also greater than equal to 0, right? Like it's not where is it, it's not minus 1. Yeah, we also have to make sure of that. In all these conditions, what we are going to do, simply continue. Okay, see, it's a lot of implementation in a single question. Okay, now like this is skip condition. Now we'll have a boundary condition. We'll do that later, of course. P dot x is equal to n minus 1. Okay, zoom in a bit. P dot y, like if we reach the boundary somehow, we don't, like it doesn't matter which boundary. I'll just, so we'll take care of this later, right? Like this is just the main part. Like if it's not the boundary condition, it's some particular case, we are just going to mark the time p dot x, p dot y is equal to what? T. See, we are marking the time after we pop the node, not before. After we check that it is valid or not. And what's the path going to store here? For int I is equal to 0, I is less than 4, I plus plus. It's going to store like the direction, simple direction, that doesn't actually matter. Now we'll like go to other nodes from that particular, like basically what we have been doing in this till now. And new y is equal to p dot y plus dy of I. And then q2 dot push. What we are going to push? Okay. Nx and y time plus 1 comma direction, right? So which direction we took? Yes, we are marking the direction by 0, 1, 2 and 3. Yeah. Now this is the most important part. Before we fill it, just fill the answer. Let's, like the string answer, we are going to store the answer. So if the flag is true, right, we can reach it. We'll mark the flag inside. We'll do yes. We'll write everything in the ternary operator. Yeah. So let's say endl to go to the next line. And what else we want to print? To string the size. answer dot size. Okay, fuck. Answer dot size, and then plus what we are going to again print, another backspace n plus answer. That's it. Else we are going to print no. I think this is a right syntax. Yeah. So just printing yes, size, and the string answer. Now how we store the answer, right? Basically what we have been doing till now, like this is, we reach the boundary or the answer, and we also have to stop the BFS, like BFS, DFS, whatever we are doing. So okay, like basically first we are going to, when we reach, we also have to mark this index, right? Path of p dot x, p dot y is equal to d, and we'll do what we have been doing till now. While p dot x is not equal to s dot x, or p dot y is not equal to s dot y. This is just for storing the path. And okay, sorry, this is going to be not s. So basically we have the path, then we are going to reverse the path, like we always store in the reverse manner, right? Answer dot end. After reversing the path, we are mark the flag as true, and then we break. Simple. Okay, so now what we have to make sure, there is one more thing. The x coordinate is for rows. Okay, x coordinate is going to be for rows, and y coordinate is going to be for columns. Like keep in mind, because it's generally confusing. Like I had this confusion in the start, so I'm just telling. Because generally we take x coordinate as a horizontal line, which should be the column. Y is for columns. Okay, we'll write ternary in one go. So basically, as we done, like if it's 0, what 0 is indicating? X 0, y minus 1, right? So same row, we are going to the left, right? Okay, so answer plus equal to path of p dot x, okay, p dot y equal to 0. If its path, current path with which it came is 0, then we are going to mark it as L. Else if path of p dot x, p dot y is equal to 1, we are going to mark it with R. Else if path of p dot x, p dot y is equal to 2, I think left, right, then it's going to be up, right? It's going to be up, else it's going to be down. Okay, so also like we had to subtract or decrement. So instead of ternary, we'll just write normally here p dot x, p dot y, which is equal to 0. If it's 0, right, what is happening is we are going left. Left is like denoted by the y coordinate. So we are going to p dot y plus plus. Else if, okay, I'll just copy this much. I'm not gonna write it again and again. Okay, what it pasted. Control C. Okay, so what it's equal to 1. Okay, so p dot y minus minus. Else if it's equal to 2, then I think it's for up. We again have to do p dot x plus plus. Else if it's equal to 3, we have to do p dot x minus minus. Okay, so hopefully, I pray to God, this will get submitted. I don't have the energy to like go through all of this again, which I think I might have to, because it's very rare to get submitted in one go. Okay, so it is partially submitted, then I am willing to even see. Okay, something is wrong. I'll just take a look. Okay, we just had a little error. We had like -1 like interchanged. So that's it. It also got accepted. So like it's really amazing. I actually wrote all this in one go and it got submitted. Just the issue with like we are going opposite now. So -1, 0, it's going to denoted by up. So I'll go through this question once again as it's a bit complicated. Like it's not complicated, but like it is a bit complicated. Just the implementation is bit too much. So we'll basically start. We are taking in the input string everything. We are going to mark the position of the starting index and the monsters. Then from monsters we are going to do a multi-source Bfs, right, to mark all the time it takes to reach them. Then from the source, what we are going to do, like whatever we'll do a Bfs, and if we'll check that position can be reached, then we are going to check if it's a boundary position or not. If it's not a boundary position, then we are simply going to continue the Bfs. If it's a boundary position, then we are going to like find the path. Like yes. So with this, our Bfs DFS section is complete, I guess. Then we'll be starting with the like algorithms part, like the Dijkstra, Bellman Ford and everything. So this was actually a very good questions, the monsters one. Like 7 questions took me like 1.3 hours, 1.5 hours. Like I was also explaining now along with, so it like slows down you a lot actually. So let's start with the 8th question. So we are n cities and flights. Your task is to determine the length of the shortest route from route node to every city. So what we are given, M lines ABC. So ASSP. So this is just okay. Now we'll get to know a bit about Dijkstra here and directed graphs also. So let's get started. I think okay. So this is just what basic Dijkstra implementation. I think the spelling is right, hopefully. It's also known as, okay, I'll decrease the side, SSSP, single source shortest path algorithm. Like currently we just want the shortest path from the single source. And I think currently we don't have any negative edges, right? Yeah, it's 1, 2, 3, so there aren't going to be any negative edges. So what's the algorithm here generally? We'll start control tab. Okay, sorry. Control L, control, okay, again, sorry. Control L, tab, yes. We'll start with vertex, like we took the source, then we start with the vertex, which is closest to source, right? Optimize length of all paths through the vertex. First we took the minimum vertex, which is at a minimum distance from the source. Then we optimize length of all the paths passing through the vertex. Yeah. Then what we do, when we optimize all paths through a node, we never look at it again. Optimize all paths through a node, we never look at it again. Okay, so like what's the time complexity? The time complexity, it's going to be O of n square, like we are v square, like we are going to visit everything 2 times. But if we use a min heap, or you can say a priority queue, if we use a min heap, also a priority queue, right? So it drops down to, I guess it was v plus e log v or something like that. Yeah, you can see in the internet. I'm just writing, I don't remember properly. Okay, so yeah, that's it. Anything else? This or time complexity algorithm? I guess limitations, yes. limitations. What are going to be the limitations? First limitation is like we are doing greedy, right? We are just doing greedy here. And we never look back. Second limitation is going to be, I think we should have this on here. Greedily doesn't work with negative cycles. We have to use dynamic programming. That's it. So this was just about the basic Dijkstra. Like it's a simple algorithm, very simple. We'll just like we'll have a infinity here. Like this infinity is going to be really helpful just to store the distances. Now let's start. Basically in n and m we are going to take in the number of nodes and the number of edges, and we'll have a vector of, okay, I don't have anything defined. We'll have a vector of pair, right, of int comma int adjacency list of n plus 1. So what we are going to do, what is this actually? This, it's a dynamic array, right? I'm just for a basic clarity, it's a dynamic array, right, of rows where each index is storing an array, dynamic array, column where each index is pair of int comma int. So this is just what the above syntax is basically. So enough with that. Let's take an input. Instead of for, we can also have while, because m is not going to get used. See, if m is going to get used, we don't use this because the value of m is getting changed, right? Int a, b and c, scene a, scene b and c. Currently it's a directed edge. So like before this we were dealing with undirected edges. We have a pair of int comma int because we have to store the node and distance also. So I guess this is done. Okay, why is this showing an error? Like, how can there be an error? Like, there's no sense in this. Okay, I'll just close the window once. I'll reopen it. Okay, it's gone now. So like it's very nonsense. Okay, so okay, it's again here. We have vector of pair of int comma int of, okay, sorry, updating VS Code. Like how it's updating at 2 AM in the morning. I'll take the charger out. It's getting very hot. So overall, till it gets updated, what we generally do in this, we take a priority queue storing distance and node, and in that we push the root node, of course, and then while the priority queue is not empty, we are going to go through all the closer nodes. If its distance, like if the distance of the top node can be optimized, we'll optimize it, else we'll go to all the children, and then we'll like optimize the children distances. Okay, I'll just pause the video till it gets up. Okay, I just cancelled the update, whatever was ongoing. It was taking a lot of time. So earlier we were having an adjacency, we were having an array of this stuff. So basically we took an input. Now what we are going to do, we will have a vector which will store all the distances from the first node. We are just getting the distances from the 1, right? Like distance of 1 is obviously going to be 0. Then we'll have a priority queue. It's a min heap, right? It is going to have the minimum value at the top, and it's going to be greater. See, one important thing, when we have a self-defined structure, not int, we can't just for a min heap we have to write the whole syntax, right? Generally we can write priority queue of pq, but if we have like something like instead of int something else like pair of int comma int, then we have to take care of, you know, like this whole syntax. One more thing, the priority queue is for on the basis of distance comma node, right? But in our adjacency list we are having node comma distance, so like take care of that. Like that might get confusing. Generally first we are going to push the root node distance 0 node 1. Also we can also have syntax like this, okay? Like this is just for like extra knowledge, like push 0 comma 1, right? pq dot empty pq dot pop, like we can also do it like this instead of using the while loop. This is just for some extra knowledge. Okay, now while this priority queue is not empty, what we are going to do, we are going to do something like, before we do that, we just basically print the answer, like the distance from the root node. Cout distance of I, cout enter. So okay, now in the priority queue what are we going to do? This is just, we'll just basically apply the algorithm. Like we don't need to search for the vertex closest, as the top element is going to be you can say already the minimum distance one. What we do, int node is equal to pq dot top, and it's storing distance comma node, so we are going to do second, int d is equal to pq dot top dot first. Okay, then pq dot pop basic. See, there is one important condition, like this is an optimization. If distance of node is less than d, we are going to continue. What does it mean? It means we are already having better distance for that node. We already have better distance for that node. What do we mean? Like let's assume we reached node 5 using 2 distances, right? Okay, node 5 using 2 distances. Not like yeah, so right, like assume 3 came after, or 3 came before 5, then we also like we pushed different distances in the priority queue. 3 is on top, it will get popped, right? No worry. But then 10 will come, 10 will also be pop na. 10 will also be popped and used to minimize the distance, right? But the issue is we already have a smaller distance of this node, that is 3, which is less than the current distance, because distance of this node is going to store the minimum distance of all the possible ways to reach it. So, and like see, and node 5 has already a distance. Node 5 has already a smaller distance. This is just optimization, so we don't need to check for those values. Like if we already got 3, 5, with that 5 we minimized all the paths leading from it. But in priority queue we also have this, right? So we'll see that this distance, current distance d, is greater than the distance of this node, which is 3. So we are simply gonna like continue, like basic optimization. So like this node is already pre-processed. Yeah, that's it. Then we are going to do like we do in the normal queue, adjusting for auto child in this, int v is equal to what? Child dot first. here child dot first is going to be node, and int c, let's say the distance is going to be child dot second. Now see, the second part of the algorithm will optimize all paths through the node, right? How we optimize it? Like if the distance, right, it took to reach the current node plus the distance between the current node and the child. Okay, my bad, sorry. Okay, we are trying to optimize the child. Less than equal to what? D plus C. Okay, yes, like this. If the distance, this is the D, see, if distance of node is greater than, D is greater than this, else D is going to be equal to this, right? So we can also write like distance of node here. Like if the distance of that node, whatever it took to reach from first to that node, plus the distance between the node and the child is greater than the distance of the child, then we are simply going to continue, right? Else we are going to optimize the distance of the child. How we do that? Simply, okay, distance of V is equal to C plus D, and PQ dot push distance of V, comma V. I guess that's it. Like basic algorithm. First we put the root node or whatever node is there. We are trying to see if we have a better distance for that node. If we don't have, like if we have, then we continue. We'll go, when we reach the better distance, we are trying to optimize all the path lengths from that node. Then we'll go all the children or in the adjacency list. We'll try to see if its distance can be optimized. Then push. Like this is like basic Dijkstra. Hopefully it will work. Let's try to submit this. Okay, it got submitted in one go, like amazing. Shortest distance to, right? Okay, what's the difference between the two? So we have to determine the shortest route between two cities. So here, like DP is not going to work. Like it can work, but we have to apply for all of the nodes, right? So like from each and every node, then it will go to a large time complexity. So instead, we here will use here Floyd Warshall algorithm, right? It's okay. Let's start. Okay, Floyd Warshall algorithm. It's ASSP, all source shortest path algorithm, O of VQ. Like this is just basic dynamic programming approach. See, what the thing is, generally, like all source shortest path using Dijkstra, Dijkstra, whatever the spelling is. If we apply, it's going to be what? V star V, okay, V square, okay, fuck, V square plus E star V star log of V. Time complexity. See, it's actually better than V cube, of course, but there is an issue. But it fails for negative edges. So that's going to be the issue. Generally here, I don't think we are having any negative edge, but it fails. So we generally use Floyd Warshall in that case. See, I'm talking about negative edges, not negative cycles. Floyd Warshall works for, you can say, negative edges, but it doesn't work for negative cycle. Okay, cycle. Okay, we can, but we can modify it. To take care of that. So what's the Floyd Warshall algorithm? We will try to relax all pairs of nodes, right, using a node k. That's it. What does it mean? If we can go from I to k and k to j, like k is here is an intermediate node, right? Intermediate node. So what we do, how we like relax the edge? Distance of ij is equal to what? Minimum of distance of I comma j comma what is the distance we get while traveling through the kth node. Okay, so like this is the basic algorithm. N is 500, so 501 constant int infinity. I think there's also a way of writing infinity, like we have to write it 8 times. I think this is it. Then we are going to have a basic vector of int of dp of mxn size, vector of int of mxn size, storing infinity. Yeah, that's it. Then like this is a very simple algorithm, just the relaxation part is bit like we just have to understand that. What's the input? 435 125 139 233. Okay, so simply 4 nodes, m edges, and then what's q? Q is the number of queries, nmq we took. Okay, so okay, let's a b c. I is less than m, I plus plus. What do you do? Int a is equal to brightness increase. Int a is equal to how much? Sorry, scene a, scene b, scene c. Now what we try to do, dp of a b is equal to what? Minimum of dp of a b comma c. Like we'll currently fill the like all the edges which we can, and like we are given now from a to b or b to a, like what's the length. Also don't write in a common statement, that will cause a bit issue, right? Like dp of ab is equal to dp of ba, which is equal to c. So okay, we'll go here and see. So basically we have done the initialization part. Then we'll start rep I1 and dp of I is equal to 0. Obviously from reaching to itself is going to be 0 distance. Then we will relax through all the nodes one by one. So I'll just use the r rep k1n, rep I1n, rep j1n. I think it's 1 based indexed here, right? It will go from 1 up to that end. Basically dp of ij is equal to what? Minimum of dp of ij comma dp of dp of kj. That's it. And just we have to perform the queries, and in queries we have 2 nodes, int x comma y, scene x, scene y, and we just have to see out what? Dp of x comma y. So if it's not minus infinity, right? If it's greater than equal to infinity, then we are simply gonna print -1. It can't be reached. Like there's no way node between those 2 nodes. Okay. I think I'll just have to, there's bit operator, confusion. So this is just the Floyd Warshall algorithm, like all source shortest paths algorithm. Let's try to submit this. Hopefully it will get submitted. and it does get submitted. Amazing. Now let's go to the next question. High score. So basically see, x can be negative here, right? High score. Okay. In this question, we play a game of n rooms and m tunnels. Your initial score is going to be 0, and each tunnel increases your score by x. It can be positive or negative. You may go through a tunnel several times. Your task is to walk from 1 to room n. What is the maximum score you can get? Okay, so what we can do here, each line has negative integers this. So if x may be positive or negative, right? Okay. Dijkstra when positive edges. Okay. Negative edges. Just a minute. I'll think about it. Okay, so basically, like, we can just use the Bellman Ford algorithm here. Like, we just first I'll write a bit of theory. Okay, so generally in single source, just a minute. So in this question, we are asked to maximize our score. Yes, what I was saying is, we are asked to maximize, not minimize. That's the issue I was having. Like, if we try to maximize the score, so this question is now single source longest path algorithm, you can say. Generally, algorithm, what's the way to do it in Dijkstra? Convert, like, what's the general way? Convert all edges to negative counterpart by multiplying with counterpart by multiplying with -1, by multiplying with -1, and then multiply the answer by 1, right? Like, generally this how we should do it. But the issue here is now, like if we minimize the negative, we'll get the longest, but Dijkstra fails na on negative edges. That's the issue. So what we do now? So what we can do, when we can apply the Bellman Ford algorithm. So what that algorithm is, it's just relaxing edges, right? Relaxing edges n-1 times. And why we do n-10 times? Because when we are having no negative cycle, right, there won't be need to revisit a node. There won't be, okay, maybe you won't get it now. There won't be need to revisit a node, right? So maximum possible length of shortest source single path is n-1 edges, right? So we have to do n-1 relaxations in the Bellman Ford. So okay, now when we relax edges, it also depends on the order. Okay, when we relax, I'm just telling a bit of theory for the Bellman Ford. It also depends on order, like in what order we are doing also. But in each propagation, there is one thing sure, we will do at least one relaxation. We'll do at least one relaxation, right? So at max we'll be having n-1 relaxations, and if no negative cycle is there, then our answer after n-1 relaxation is the final answer. And time complexity is, I think, V star E, number of nodes into number of edges. And what? Also, there's an like extended Bellman Ford, you can say, algorithm. What it does, it resolves negative cycle single source shortest path in 2 star V star E. Like we have to do like everything again to like resolve the negative edges. So that's it. Like in BFS, see BFS when we have no weights, basic Dijkstra J I think. Dijkstra we do when we have positive weights, and Bellman Ford we do when we have negative weights, and cycles also, but it has to be optimized a bit. I think, yeah. So okay, in this problem, okay, even if there is a cycle, right, a cycle in graph, like but not part of path between vertex and way, between the vertex 1 and n. Yeah, it's tolerable, right? Is tolerable. So what we can do, yeah, like that's it. Okay. Like just like this is just the basic theory is done. I think there is nothing else to write. So initially, let's create again a struct for this tunnel, right? In starting index, finishing index, and the weight of the edge tunnel, whatever it is. Now go to the let's go to the main function. So don't mind the theory, like this is just for saying, like maybe you won't understand a bit of it. After some time you will say in n and m we are going to take the number of nodes and edges, and basically vector of int of distance of n plus 1 infinity. I think I haven't wrote an infinity yet. Constant int infinity is equal to how much? 1e 18. So this is going to be the infinity. And we'll have a vector of tunnel, a struct which we created. Let's call it edges. It will have m size because there are going to be m edges. And then for auto, here we have to apply ampersand. It's important. Like we are passing by reference now, like those values. So we are just going to take the input of that struct, e dot s, e dot f, e dot w, right? And then we'll multiply the like weights with -1. Also, tunnels are unidirectional. Right. And similarly, distance of 1 is equal to 0. You have to maximize the distance. Then we'll have a Bellman Ford which will take care of the distance vector. Now what will happen if n is equal to 1, right? This is just a base condition which is very important. Okay, I'll take care of it later. Like mostly probably a test case will going to fail, then I'll take care of it. Then what you're going to do, if distance of n is equal to negative infinity. Negative infinity here is, okay, I haven't formed it. Negative infinity is just you can say -1 star infinity. It will work, right? Why is the color okay? So if the distance is negative infinity, which means We can't reach it, right? So basically we are going to see out -1, else what you are going to see out is -1 of answer. Okay, now we just have to write this Bellman Ford algorithm to relax the edges, to relax using the edges. I think it is going to be void Bellman Ford. Also we are going to take distance by reference, as we are going to manipulate the distances as we go on. Tunnel ampersand edges vector int of ampersand distance. Okay, so basically we'll do basic relaxation, as they are going to be how much for each node. What we are going to do for not each node, for n-1 number of times, we are going to relax using the edges for auto ampersand a in edges. What we're going to do, if like first node is going to be e dot start, like the second node is going to be the e dot finish, and weight is simply going to, let's say d is equal to e dot w. How we optimize this? If distance of like the previous node is not equal to infinity, like if it can't be reached, how can it be used to minimize the distance, right? If we can't reach it, if we can't reach u node, right, till now, we won't update v using it. Okay, I'll also put the laptop on charge. I guess this is going to be a very long video. So if the distance of u is not equal to infinity, which means it can be used to minimize the distance of v, so we'll try to minimize it. That's it. So how I did this? This distance of v is equal to maximum of negative infinity comma minimum of distance of u plus d comma distance of v. Inner part is, see, generally we don't need this much, just function. Okay, generally we don't need to do this much. What we are doing is this is just to make sure that our answer does not go below -infinity. Here it won't go, of course. Like if it goes below -infinity, we'll try to bring it back to negative infinity, right? That's it. And then what we'll do for negative cycles, okay, we'll again run the relaxation n times. Okay, same for auto ampersand e edges. I think we can also copy. I'll just write it, doesn't matter. Dot w. If distance of u is not equal to infinity, then what we are going to do, like here what we are going to do, distance of v is equal to what? Maximum of, here we are doing that relaxation with negative infinity. Or we can say like if distance of u, right, plus d, if it can again be relaxed, distance of v. Now we'll mark it with -infinity, because we don't want it to be relaxable anymore. Means the answer, if it can be relaxed more than n-1 times, which means infinity, it should not be able to relax, then we'll mark it with negative infinity. Okay, I'll say it again. If it can still be relaxed, we will mark it with minus infinity. This is just to show that we can't reach this position, or like it's a negative cycle. That's it. This condition is also to make sure it doesn't go below the, but we don't need it now. Hopefully it will work. Yeah, graph algorithms, like there's a lot of implementation, like in BP and other playlists which I'll be making, they're going to be this much implementation. Okay, let's submit this. Okay, here's the wrong answer. How's the wrong answer? Okay. Yes. So what I was saying is this one. What if there is a loop on 1 itself? Yeah. Okay. We have to take care of the condition. If n is equal to 1, we check the condition for other loops. But what if there's a one node and we are only having loop on it? Its weight is less than 0. Cout minus 1 enter. What I am saying is it's a self-positive loop. So the score keeps on increasing. That's it. If this is this, else we are going to go in this loop. So this question is a bit difficult. Like it's like advanced, not advanced, a bit typical version of Bellman Ford, like a very good question, you can say. Like one of the best questions there is. Okay, so it got accepted. Now flight discount. So this question, what you are given. Okay, let's start this one. How much time it has been? It has been around 2 or 30 minutes. Nice. Okay, flight discount. So we have to find them. Okay, so this is a Dijkstra, same question. Just the thing is, we have to use a discount coupon whose price is X, it becomes X by 2. Same question, I think ABC input, N and M. So here we'll learn the concept of State Dijkstra. Okay. What we'll do, we will use State Dijkstra. I think it's Dijkstra, whatever. Dijkstra here, right? We process each node as a state. So what we do, we just carry a flag to see if the coupon is used or not. We just carry a flag to see if coupon is used or not. That's it. Same Dijkstra, same procedure, just a bit of modification. Thus, State Dijkstra. Constant int infinity, which is equal to 1e18. Void Dijkstra, and I think we have to pass what in the Dijkstra? The graph and the distance, right? Void Dijkstra. It's what it's going to be here. Yes, I have already written it. VPI ampersand. Yeah, don't mind this. VPI ampersand distance. Oh, so this is like the basic template for the Dijkstra function. We'll get to it, don't worry. We'll take the number of nodes, number of edges. We'll make a vector of pair of int comma int adjacency list, like not list, whatever this will be called, and we'll have a vector of pair of int comma int distance n plus 1 comma what we are going to store in it, infinity comma infinity. I'll explain it to you once again. So we'll have a distance vector which will have two, like we have a distance vector here which is having two indexes at each instance. What that instance is showing, that if at this state we have a coupon, what is the minimum distance still here? If at this state we do not have a coupon, what is the minimum distance we have till here? So the 0 index is for with discount, 1 is without discount. That's it. For int I is equal to 0, comma a, comma b, comma c, I less than m, I plus plus. We are going to take in the edges. I think they are directed. Yeah, they are directed. It's a flight question, so they are going to be directed. Okay. So what we are going to see? First, we are going to distance of 1 dot first is equal to distance of 1 dot second, which is equal to 0. Obviously, even without using the coupon, we are at the first position. So then we are going to run the Dijkstra, passing the adjacency list and distance. And in the end, what we are going to see out distance of n dot. We have to use the coupon, right? So first. Now let's write this function. This is just going to be the same function. I think let's have one more macro here has defined pair of int comma int as PII. So we'll have a priority queue. I think there is going to be one more pair. Yes. Okay. So okay, it's getting complicated a bit. I think it should be called PIPII. Yes. So we'll have a priority queue of PIPII, vector of PIPII greater. Okay. It might be a bit intimidating, like these questions in the start. Actually, it might be a lot intimidating. So like, but with time, they actually get very easier, hopefully. So PQ. I think the syntax is why the color is not getting changed. I don't know why it's not getting changed. So what the first in storing the cost, another showing node and coupon. That's it. We'll obviously try to run the priority queue on basis of cost and then the coupon also, right? So initially pq.push, what we having 0 as the current cost, node is going to be 1, and we already have one coupon. We have coupon left, right? Okay. Now we are going to run till the priority queue is empty. Okay, so what we are going to do, basically as we have always done, d pq dot top dot first. This is going to be the cost and node. Let's say int node pq dot top dot second dot first. Okay, and then the coupon. Let's say it's c pq dot top dot second dot second, right? PQ dot pop. Okay, so okay, like okay, basically like the optimization we did in basic Dijkstra, right? We'll also do here. What is the optimization? If we have more than one occurrence and we have got better distance, so we will skip other occurrences, right? Basically if c is equal to 0, we don't have a coupon, and then we'll see if distance of that node is dot first is less than d. Like the first is used up coupon 1, then we'll continue. If we are at that node where we can still use coupon, then we'll check if the distance of node without the coupon is less than d, current distance will like continue. So this was just basic, you can say, optimization in the priority queue just for better time complexity. Now we'll go to the all the child in the adjacency list of that node. So int v is equal to child dot first, distance is equal to child dot second. Okay, so like there are two cases, right? If we are in the case where we can use the coupon, so c is equal to 1, else we are the case where we can't use the coupon. If we can use the coupon, right, it's not necessary we use the coupon. So what we are trying to say, if distance of v dot second is greater than d plus distance, right, else if distance of v dot first is greater than d plus distance by 2. See, we are trying to decrease the distance of vth node, right, from the like source node. This case is okay. We don't use the coupon. We use the coupon. Okay, so distance of v dot second is greater than this, so we just dot second is equal to d plus distance. That's it. And also distance of v dot first is equal to d plus distance by 2. And then we again put the node in priority queue. Distance of v dot second, comma, what's the node v, and we can still use the coupon. pq dot push distance of v dot first. Like we are doing like passing two different types of distances together, v comma 0. So if this is for the case we have the coupon. If we don't have the coupon, basic distance of v dot first is greater than d plus distance. We can't use the coupon na, like we don't have anything, so simply distance of v dot first is equal to d plus distance. If it can be optimized, we'll optimize it. And then in the priority queue we are going to push first, comma, v comma 0. I think this much is it. Basically we are having State Dijkstra, we are optimizing, and if we can use the coupon we are using, otherwise we are not using. Let's see if it will get submitted. Huh? Okay, what's the issue here? VVPII. What's the issue here? Okay. Sorry. Lol. I think we have to write it first. Now it will get colorful, I think. Yeah, now it will get colored. Okay, it didn't got colored, but let's try to submit it again. Flight discount. Yeah. Here it's going to be this. Let's try to submit again. Okay, it got submitted. Right, nice and amazing. Now let's go to cycle finding question. You are given a directed graph. You have tasked you to find out if it contains a negative cycle or not. Okay, how many questions are there of this type? Flight routes, round trip. I'll just take the round trip to course schedule, game and investigation. Okay, let's start with the cycle finding one. Okay. So it's a question regarding negative cycle, right? So we have to do what we did earlier, like mostly the same. Okay, so let's start with the 12th question. I'll just write a bit of theory first. I'll just tell instead of writing. So when we run Bellman Ford like 2 times n minus 1 relaxation, we get nodes with minus infinity shortest paths. Just give me a minute. Yeah, I'll just write everything. I'll pause the video and write first. Okay, so what is that? When we run Bellman for like 2 times n minus 1 relaxations, we get all the nodes with minus negative infinity shortest paths. But if the source is disconnected from all the vertices, then all distances are simply infinity. But still there can be negative cycles present. So what we can do, we can take an imaginary node and connect to all the nodes with zero distance, mark all the distances as 0 and relax edges as negative edges. So this is the for the case of negative graph. The nth iteration can result in the relaxation of edge which either belongs to the negative cycle or vertex to which the negative cycle is leading to. But we want this vertex to be a part of negative cycle, right? So we can just cycle through to Pintor cycle. That's it. So we pass the parent of a node also which relaxed it. That's it. So if a particular vertex got marked as minus infinity, its parent is the reason for the relaxation. So if we keep tracking back, we'll keep going back. Worst case n minus 1. Example, node 1 has negative cell cycle. We need to track back from the last node. We continue to track back relaxants until we end where we started. So after another iteration, if we confirm negative cycle, we start from the vertex which was last relaxed and we trace it relaxant n times to confirm that we are in a vertex that's part of a negative cycle, and we continue to trace back relaxants until we end where we started. Yeah, that's it. Then we reverse the order and pen the cycle. Like the procedure, let's initialize Bellman Ford with all distances as 0. Relaxation will take us to negative distances. We can perform n iterations. We capture relaxing parents, and nth iteration will confirm or deny the existing of negative cycles. That's it. So this is a bit of advanced question compared to other ones. So if it's bit, you can actually skip that. You can actually skip this one. Like it's a bit, like it's actually a lot advanced. So you guys can skip this one. So we'll have a struct of trio M, right? We'll have a like CNN M. We'll create a vector of trio of edges of n, right? And vector of int of distance of n plus 1 comma 0, vector of int of parent n plus 1 minus 1, right? That's simply the relaxant or the parents which are going to be. And then for auto, we are going to take the edges. Ampersand e in edges. We can just do here also. It doesn't matter. Same e dot s, e dot e, e dot w, and then we are going to have a function Bellman Ford which will take the edges, the distance, the parent, right? Okay, so void Bellman Ford will pass the struct we created for the edges, int of okay. So let's start int. So int node, like okay. First what we'll do, we'll try to run it up to n times. Why n times? Because if in the nth time, it can still be relaxed, then only we have the possibility of a negative cycle. For auto, ampersand E, like just pass the E edges, right? Like all E dot S, E dot E, D is equal to E dot W. If distance of U plus D is less than distance of V, distance of V is equal to D plus distance of U, right? So this is like basic relaxation, and parent of V is equal to U, by which it was relaxed, and node is going to be V, the current node, the relaxed node. So we'll take a node here, int node. If node is equal to what, like minus infinity, if like for each iteration what we do, we reinitialize it to -1. If node is going to be -1, right, so we are going to see out no. Means there are no you can say negative, I think negative cycles, yeah. Else if there is a negative cycle, what we are going to do, we are going to go to the nth parent of this relaxed one. Node is equal to parent of node. So this relaxant is obviously going to be part of the cycle, the part of the negative cycle. So vector int of answer, like this is a basic, like we did track backing till now, while you can say parent of node is not equal to node, right? We already put the node, so answer, in the answer we'll be pushing back parent of node, right? Parent of node, parent of node, as I'm modifying the parent array because we don't need it anyhow na? In the answer we again push back the node because we have to complete the whole cycle. As obviously we know, we always have to reverse it because we are in the reverse direction, parents, we want to like opposite direction, and after reaction simply you see out like in all the see out yes, then I think we don't have to write the size here, right? Okay, so we are going to see out yes, and then yeah, and then for auto ampersand V in answer, we are simply going to see out the V, that's it, and then we are going to see out the and then yeah. I think it will get submitted, hopefully. It's simple, that's it. Okay, we are getting some wrong answers. The wrong answers are generally where we are getting no in all the cases. So let's see what's the issue. Basically we are taking in n and m as input, right? Vector of int of distance of n plus 1 comma 0, initializing all the parents with -1. For auto ampersand we are taking in the edges, good. And then we'll go to the Bellman Ford algorithm, we initialize the node. We'll go to all n iterations. If for we try to relax using those edge, node is equal to v. I think this much is good. If node equal to -1, we see out no, else we have a cycle, then we have to run till n times, right? So vector of int of answer, right? Answer dot pushback node, while parent of node is not equal to node, answer dot pushback parent of node, and parent of node is equal to parent of node. Then we again push back the node, reverse answer dot begin, see out yes. It should be working mostly. I don't know what's the issue generally. Okay, I actually don't know what's the issue. See, it's printing no. instead of why it's when it's printing no. If node is equal to -1, for I1 less than equal to n. For auto E in n is E is equal to E dot S, V is equal to E dot A, D is equal to E dot W. Let's try to see out node at every instance. Here, see out node. It's turning into a more of a live stream than a explanation video. Never mind. Okay, how are you even getting the right answer? 3 4 3 4 5 1 2 3. So it should be right now. 4 5 1 6 है 4 5 1 6 no 4 5 1 6. Okay. 1 5 4 3 2 1 1 5 user output 1 5 4 3 2 1. Okay, so 1 5 4 3 2 1 5 4 3 2 1. Okay, just a minute, I'll see what's the issue here. Okay, so we had to like edges should be off, and like a very stupid mistake on my end. So let's remove this. Let's see if it's working now. Yeah, actually this question is a bit advanced, like too advanced. Like not too advanced, but the theory part, like it takes time to understand. So let's submit this one. Yeah, cycle finding. Okay, it got accepted. Now let's go to the next question. Flight routes. Your task is to find k shortest flight route. So this is just Dijkstra, but it's like a bit of modified, like where we have to store an array, or you can say a DP. If we get a new better distance, we just optimize in that DP. We have to find k shortest routes, right? So it's going to be a k single source shortest paths. Yeah. For each node, what we are going to do, for each node we are going to store k lengths, right? We are going to store the k length, going to store k lengths. That's it. Okay, for each node we are going to store k lengths, and what we do, we just keep updating the worst current path and sort them. We store path in order from best to worst paths. That's it. We just keep updating the worst current path, right? If we get a more worst path and sort it, basic, like after sorting we'll have a worst path. If we get a even worse, like what we want in the k shortest flight routes, right? So we'll have the worst path. If we have a less worse path than it, then we'll bring it in. So, and we store what? We store path in order of best to worst paths. So okay, we store in the best path. Here is shortest to longest, and if we have a path which is less than the longest, we'll just replace it. And then we again sort it, so it comes back to its own position. We'll have n, m, and k, number of cities, and the k, what's the k? K is the size for the DP. M, k. So constant int infinity is equal to 1e 18. Okay, so we'll have a Dijkstra. We'll take care of that later. First, let's take an input c in n mk vector of pair, yes, adjacency of n plus 1, right? Vector of distance n plus 1, vector of int k infinity. Yeah. So what we did, we created a distance vector which will have n plus 1, like 1 up to n nodes, but each node can have k best distances. As if for each node we have to store k distances, and what for 0 all are going to be 0, I think. Distance of 0 I equal to 0. For int I is equal to 0, this is just basically taking in the input. So adjacency list of a dot pushback b comma c. And then we have a Dijkstra function, Dijkstra Dijkstra. We have to pass the edges, of course, adjacency list and distance. And then we will just, like, for int I is equal to 0, or we'll like print all the k distances for the nth index. Cout distance of what? N comma I. That's it. Okay, so let's start the Dijkstra now. What will have VP, VVP, II, I think, yes, of adjacency list, and distance is going to be what? VVI, VVI ampersand distance. Priority queue of what? We'll be having two indexes, right? The distance and the like k, I think, like all the k ones. Cost and destination, I think, yes. Cost and here's its destination. Yeah. So PII, vector of PII, and greater of int of PII. Okay. So our priority queue is ready. Now in pq.push, what we are going to push? 0, 1. The cost which we push and the destination. Like, to reach that particular destination, what was the cost required? And basically, what we have to do, while pq.empty end node is equal to pq.top dot destination, I think, second, and int distance is equal to pq.top dot first, and then we'll pop the element. Okay, after popping the element, yeah. Okay, so what we are going to do now, like, we'll check, like, we don't have to check for the optimization for all the distances. We'll just try to see the distance which is the most worst. Obviously, if like the most worst distance is if the d value is even greater than the most worst distance, we are going to continue, right? Then what we are going to do, we are going to go to all the childs of this in the adjacent list of this node, and then what we are going to do was, okay, int v is equal to child dot first, and d is equal, I think we use d, let's say distance is equal to child dot second. Okay, we didn't use a semicolon here. I should have a macro f for first and s for second. So what I was saying, we'll see if the last distance, right, if the last distance is greater than the d plus distance, if it can be optimized, then what we are going to do, we are going to replace the I think it's going to be v, sorry. Then we are going to replace the last distance, like the worst distance, by a distance which is better than it. So d plus distance, and then we are going to again push it in the queue, pq dot push what? Distance of v, k minus 1 v, and then we are going to sort it. Distance dot begin. Okay, to tell the truth, I'm actually very tired. Okay, it has been a lot of time now, so we'll sort the distance and we'll just push and sort. I think this is it, like basic Dijkstra with like k states we have to store along with it. Flight routes, let's try to submit this. Okay, hopefully it will get submitted as I'm very tired now. Okay, it's going to give wrong answer again. What's the issue? 10E9, 1E9, how many nodes? 1E5. So that doesn't matter actually. In the priority queue, we initiated 0, 1 while PQ is not empty. Node is equal to PQ dot top dot second. Distance PQ dot top dot first will pop it. If the distance of k minus 1th is less than d, will continue. Auto child in adjacent list of node. If v is equal to child dot first, distance is equal to child dot second. Distance of v comma k minus 1 is greater than d plus this. So we upgrade distance of v comma k minus 1. And in the priority queue, we push the distance of v comma k minus 1 comma that node v. We'll sort distance. Okay, we are sort. Okay, that's the issue. We have to sort for that particular index now. Of course, why are we sorting everything? I think that is giving TLE, right? Like that is like doing a lot of iterations now. Like a log of n star k iterations. Okay, so that was not it. Nope, that was also there. That was not the main reason, I think. What's the answer? We are getting wrong answer. Something is getting printed, right? User output. Okay. User output, we are just getting one number. Is it? It's long. Okay, so priority queue of PII, vector of PI, greater of PII, बिल्कुल सही है. Infinity if I take as 1 is 17. Yeah, I don't think that's going to do anything. Of course not. Like that doesn't even make sense. So flight routes. Okay, so what's the issue? Constant infinity 1 is 17. Will push in the priority queue 0, 1 while PQ is not empty. Node is equal to PQ dot top dot second and D is equal to PQ dot top dot first PQ dot pop. The distance of node k minus 1 is less than D. Continue. For auto child in the adjacency list of the node, into E is equal to child dot first. Distance is equal to child dot second. If distance of v comma v is greater than d plus distance, then we'll upgrade the distance. That's it. And then pq dot push distance of v k minus 1. Okay, so we'll sort the distance of v dot begin. Okay, so it worked. Okay, so it was just some issue, I guess. Okay, then let's go on to the next question now. Round trip 2. Byte has n cities m connection. Your task is to design a round trip that begins in a city, goes through one or more city, and finally returns to the starting city. Every intermediate route has to be distinct. So we already did one. I think let's go up round trip 1. The difference was NMA. Okay, there's something else here also. What's the difference between the two? Okay, round trip 2 is for directed graph. Okay, so like this is a very simple question. Now easy questions are finally starting. Oh, okay, we'll do it fast. See, round trip 1 was in undirected graph. So what we did in undirected graph, we DFS when we encounter a already visited node which is not parent, we get a cycle. But in directed graph, it's not necessary that it's a cycle, right? So what we do in a round trip 2, we simply what we do in this question, we simply simply while doing recursion, we push elements right in stack, and if we have encountered an already visited element, and if we have encountered an already visited element, it's a cycle. We have to make sure that the current element is also in the recursion. That's it. Do we have to print them also? Yes, we have to. Okay, we have to print the solution also. Okay, still it's going to be comparatively easier than the previous two questions, like the Bellman Ford optimization and other one. Basically, let's create scene n m. We'll just create everything here, no global anything. We'll pass it, no bullshit anything. Vector int of visit. Here it's going to be n+1 and vector bool of flag n+1. In we'll have a stack of integers, basic, and then for int I is equal to 0, x, y, I is less than m, we are simply going to take all the edges in first, scene x, y, no time waste. Yeah, I think we can write it like this also. Okay, so as the directed edges are going, they are going to be directed edges, so we'll call a solve function, and it's going to solve. We have to pass the adjacency list, the visited, the flag, and what, I think stack also. Yes, so this will solve us. Now what we see, now on solving this, what we should get some values in the stack, which is the cycle. So we got, if it's empty, which means there's not a cycle, so we just see out no or impossible. We just see out impossible, see out impossible. Okay, and then we return 0. Yeah, that's it. Okay, so and then we'll have a vector of int of answer. We'll just do what we have been doing till now. In source is equal to s dot top, right? Okay, and answer dot pushback source and s dot pop, right? While s dot top is not equal to source, we're simply going to push back in it. Answer pushback s dot top, and then we are going to keep popping it, popping till we get, and in the end we again push s dot top, answer dot pushback, like source. Yes. Okay, so with this, then we will just reverse answer dot begin, answer dot end. Yeah, after reversing, we'll just see out the, we have to print the size, number of cities. Yes, see out answer dot size and L, and then we have simply print all the cities for auto IT in answer, see out IT. So this is just a very basic question. Now we have to write the solve. Solve, it should be a void function, right? Instead of solve, what we can even do is we can just make a okay, let's have a solve function. Yeah, it's good. We have a solve function. We have vector of int of its written macros, right? We don't need to pass it by reference, as arrays are already passed by reference. Vector of int of flag. Okay, yeah, so that's done. Stack of int of ampersand s. Then we'll go for int I is equal to 1, I is less than equal to n, I plus plus, yeah. We'll go through all of the nodes. If it's not visited, right, we'll visit it, we'll do a DFS. If the DFS returns true, which means DFS adjacent list visited flag, which means we simply got our answer. We don't need to do it anymore, right? Now we'll create a DFS, bool DFS. We'll have the current node, vector int of adjacency list, vector import ampersand visited, vi of ampersand flag, stack int of ampersand s. Okay, so obviously as we do in DFS, first we are going to visit the node, then we are going to push the node. We push the node in the recursion and we'll make the flag of node is equal to true, which to indicate that it is currently in the recursion. Then for we'll start for auto child in adjacent list of node. We'll do like DFS. When we return back from DFS, then we are going to pop it, and also flag of node is equal to what? False, to show that it is not in the stack anymore. That's it. And then return false because we're with the traversal and we did not got any cycle. So for that connected component, there is no cycle present. Else what you're going to do, if the child is not visited, simply DFS and if okay, I'll just write it in here. If the child is not visited and if its DFS is returning as true, we simply return true. That's it. Which else, if the child is visited, we'll see if it has flag or not. If flag means that it is already in the recursion, then we are going to paste the child in it and then simply break it. Okay, that's it. Okay, now I also have to speed up a bit. Round trip 2. Hopefully it will get submitted. So that's it. If flag is there, which means the child is also in the currently. Okay, there is an error here. What error? Okay, vector of int, it should be vector of boolean. There is still error. Now what error is there? Okay, here it should also be vector of boolean, yes. Where's round trip 2? Okay, there is runtime error in some. This runtime error in everything here. Now, what's the issue? See, basically the solve function is right. For int I equal to 1, I less if it's not visited. If DFS will return true, we'll give a break. As we don't have to return anything. In the bool DFS, what we are doing, simply visiting the node as dot push node and flag of node 2, and while returning we'll pop it, flag false, return false. And for auto child in this, if child is not visited, we'll do a DFS from child, yes, and if flag of child equal to, which means s dot push child, and then we break. We don't have to break here, we have to return true here. Okay, so that was the issue, I think. Okay, I think with this our these algorithms are also okay, I think there is some issue again. Let's see. Okay, so in the main function, vector of int or adjacency list n plus 1 size, good. We took everything as an input. We call the solve function if stack is empty. So we'll see out impossible. We'll return 0. Otherwise, we'll make a vector int of stack source equal to s dot top, answer dot pushback source s dot pop. While the source dot top is not equal to source, I think it should. I don't know what's the issue here. Okay, like what the nonsense is this? Like fuck. Okay, so with this we have completed the basic part. So this is course schedule. This is a very famous basic question of topological sorting, I think. So I'll give you a brief introduction about topological sorting. I think after this longest flight route, this question if there is a list of cities, we have to make sure. Okay, so where were we? So this is a question of basic topological topological sorting. We have to complete n courses. There are m requirements of this form. Course A has to be completed before course B. Our task is to find an order in which you can complete the courses. Okay, so like that's it, basic question. Let's start with this basic topo sort. This is going to be a basic implementation of topo sort. So what we do, topo sort is generally for directed graphs, directed acyclic graphs, I think. What does topo sort gives us? A linear ordering where A comes before B if A there is a like node from A to B. So basically if you have to do one task before the another, so there like it will come before in the ordering, right? Sorry, like A can only be done after like I think it's like one way or another. Yeah. So in degree, what's in degree generally? Number of edges leading to that vertex. Leading to that vertex, right? Like when we remove like 0 in degree 1, right? So what we are going to do, like in the topo sort, first we start with the 0 degree ones, in degree ones, and then when we do that, we reduce the in degree of all other connected components, right? So remove 0 in degree in degree ones and reduce in degree of all other connected components. Yeah, that's it. So this is just basic topo sort implementation. Like we can use Q stack, I don't like anything, so we'll just take in an as an input. We have then m edges, right? So we'll have a vector of int of in degree. First initially all in degrees are 0 because we have not connected the nodes yet. Then vector of int of adjacency list of n plus 1, right? For int I is equal to 0, a b I is less than equal to I is less than m I plus plus. Yeah, so what we're going to do, we are going to take in scene A, B, adjacency list of A dot pushback. We are going to push back B in it, and then for B we are going to push back A in it, and then in degree of B plus plus. Yes. Okay, then we are just going to do topo sort. Topo sort with it adjacency list and in degree. That's it. And we have a basic topo sort function, void topo sort vector int of adjacency list this vector int of ampersand in degree. So okay, we don't even need a priority queue here. We can just use a normal queue as everything is increasing by 1 1 1. So we'll just have a queue. What we initially do, we'll have a vector int of answer also. It will solve everything in this one. Initially for int I equal to 1, I is less than equal to n, we'll go through all of the nodes. If in degree of that particular node is equal to 0, we simply push the in degree 0 ones in the queue, right? We'll do something now while the queue is not empty. Okay, after we return from that, see if answer dot size equal to n, right? Then we can form a topological sort and we can do whatever we wanted to do, right? Properly. Means all the elements can be fitted in the topological sort. There is no uncertainty that what we have to do before comes like before in the understand na? If you have to do A before B, but in the graph it's B before A. So if there is no uncertainty like that, we just simply print it. Otherwise we just print impossible. That's okay. Okay, so int node is equal to what? Q dot front, yeah, Q dot pop, and then answer dot pushback will push back that node in it, and then simply for auto, what? Auto child in adjacent list of node. Simply while we go through, we are going to reduce the in degree of the child as we are going to remove that node from the queue. And if we get a child such that its in degree is equal to 0, we are simply going to q dot push child. So this is like very basic topological sort implementation. So let's submit this. Okay, it got submitted because it's a very simple question. Now next question is longest flight routes. So what we have a contest and the price is a free flight that can consist of one or more flights through cities. So we want to choose a trip that has as many cities as possible, right? We can solve this one using Dijkstra, Toposort, dynamic programming, I think. So basically what we want is the longest path from a node to another node. That's it. We'll just have a simple basic dynamic dp or distance, whatever we want to say, and just keep on maximizing the dp of a node using its children. Okay, so okay, it has been 3:30, like it has been 3.5 hours already. Okay, so let's start with the 16th question now. It's a basic question, right? Well, like we just have to find the maximum number of cities. We'll just store all the maximum number of cities to reach to the nth, like the n, like from that particular dp of x, what is the maximum number of cities to reach to n, right? Okay, so let's start. First, dp of I is equal to longest path from node I to n. And do we also have to print the after this print this? Okay, we also have to print the cities now. So we'll have a, you can say, successor array to store the successor of each node, right? So basically int nmm will be doing a DFS. Before doing DFS, let's take in input scene n on m vector int of adjacency list of n plus 1 size. We have a vector of int of dp n plus 1. Initially we'll have it by -1 for memorization. I think visited initially we'll have 0 as visited. Successor 2 for having the path. dp of n is equal to 1, obviously, like this is like the base case. Longest path, there's like 1, not 0. It's not, you understand now? From that we are like yeah. So for int I is equal to 0, a b, I is less than m, I plus plus, what we are going to do, scene a b, adjacent list of a dot pushback b, adjacency list of It's a directed graph, sorry, my bad. Then we will have a DFS function. Now what we do, if we can't, for like initially if it's -1, right? If we can't reach, then simply we are going to see out impossible, else what we're going to do, like basically we have the answer stored. If dp of 1 is equal to -1, like we can't reach from the first node to the last node, then simply see out this. Else what you are going to do, you're going to see out dp of 1, which is going to store what? The maximum, the path. Normally node is equal to 1, while node exists, we'll go to the successor of the node. We are going to see out the node, and then we are going to node is equal to successor of node. Okay. Yes, we are also have to DFS. So we'll do DFS. In DFS, what do you have to pass? You have to pass everything. Initial node 1, adjacency list 1, DP, visit, successor. And then we have to just write the basic DFS for this. Int node, vector int of adjacency list, and DP is what? Vector of int, vi of %dp. We have to pass by reference, so we have to change everything. And then successor. Now as we do in all DFS, simply we are going to mark it as true, and then we are going to go to all of its children, auto child and adjacency list of this node. What we are going to do, simply if it's not visited, we are again going to do DFS. We don't have to return anything here. DFS of child adjacency list DP visit successor. So with this, our not visited is done. Now what we'll see, after we return from the DFS, right? After we return from the DFS, if you can say DP of child, like whatever is the longest part of the child plus 1, it is greater than the DP of node. Like we have found a more longer path, right? DP of node, right, is equal to DP of child plus 1. Simple. And then successor of this node is going to be what? That child. There is just one more thing. If it's not visited, do DFS. See, we haven't put a visited condition. So let's have, if DP of child is not equal to -1, and this. So if it won't reach n, okay? So we don't even need to use it, right? We can't, yeah, so that's it. Like if DP of node is equal to 0, something like that. If initially DP of node is -1, even if that's it, I don't think we even need this condition. So yeah, this was a simple DP trees question, longest route, flight route. I think it will get submitted, 99% chance. Okay, it got submitted. Now let's go to the next question. So a game is having n levels and m teleporters. Your task is to get from level 1 to level n. The game has designed so that there are no directed edges in the underlying graph. So we have to ask, in how many ways can we complete this game? Okay, so what we can do here? So basically, when we are at a node, right? If there are two ways, it is it is becoming into two ways, right? Yeah, just a minute. I'll think about it. I'll see stuff. Okay, so in this question, basically what we'll do, I think level 1 is going to have in degree 0, right? And with that, what we are going to do, we are going to do simply ways of child plus equal to ways of node, and then we'll keep on doing the you can say BFS, right? But the issue is, like, no issue, but at the start instance, like when we start the game, right, if there are already some other nodes with in degree equal to 0 that are going to also interfere with the number of ways if we go with that approach. So it's like a question of topo sort. Very good question of topo sort. As we go, we'll understand it. Yes, I think it's we have to print constant modulo. Let's start with the 17th question. Constant int mod equal to 1e9 plus 7. 1e9 or 1e19? 1e9 plus 7. Okay, now, so first I'll do it, then I'll tell. Yeah, it's more easier that way. You simply seen vi of ways plus 1 comma 0 and degree of n plus 1 comma 0. vi of list of n plus 1 for int I is equal to 0. A b I is less plus plus seen a b additional list of a dot. So basically in this question we are simply going to normally calculate the roots ways, but the issue is the nodes which will have in degree 0 other than the root node will interfere with it. So we have to make sure to remove all the unwanted edges. Like we first store all the, let's have a function topo sort. Let's have SS captain adjust ways and then in degree. Okay, so we have to simply see out ways of n. That's it, and then n. Okay, so what we have to do, like generally how it should have been. First VVI we just give me a minute, I'll code a bit. We are emphasizing in degree. Okay, first we'll have a queue, int q. In the queue we are going to push 1, right? This is how it generally should have been. Number of ways is how much? 1. We'll do in the reverse order. While q dot empty, while the queue is empty, right? Int node is equal to how much? Q dot front, then we are going to do q dot pop, and then we are also going to do for auto child in addition list of node. Simply add the ways, decrease the in degree, we will think about later. Generally this is how the solution should have been, ways of child plus equal to ways of node, right? And then ways of child equal to mod, right? If in degree of child equal to 0, then we are going to push the child. Basically simple, we are just imagine there's like simple, this is basic a chain type question now. 1 to 2, 2 to 3. So initially it's 1, but instead if there were two chains from 1, right, you can say Basically, as many chains are pointing to that element, number of ways are going to add, right? Into, like, it's like basic PNC, okay? So in degree of child equal to 0, and here we will also reduce the in degree of child. Okay, let me explain like this. If there's a node from 1 to 2, then 2 to 3, number of no, answer is going to be 1 to 2, then 1 to 3. If there's 1 to 2 and also 1 to 4 and 2 comma 4 are both pointing to 3, so the answer is going to be like you can say 2, right? As ways of child plus equal to ways of node, simply answer is going to be 2 if both 2 comma 4 are pointing to 3. And also if it's a bit different, like instead of you can say just simply if as many ways are there, we add them up and then we multiply them, like how many times they occur. Like basically like make a small graph on paper and just try to run this. But the main issue here is that the elements which have in degree 0 other than this node are also going to interfere. Yes, because if this condition if in degree of child, they're also going to interfere. Yes. Yeah, okay, so what we can do is we can start with all nodes other than 1 with in degree 0 and remove all the branches which will interfere in it. Yeah. Okay, so instead of before this we do, then you start with all the nodes other than 2 with in degree 0, and then if in degree of I equal to 0, then we are going to push it in I. Simple. While q dot empty, we have to remove unwanted edges. Simple. In node is equal to q dot front and then q dot pop, and then for auto child in adjacent list of node, what we do, we decrease the in degree of that child. If that child in degree 0, we push that child back into the stack, but we have to make sure that child is not the parent. If child is not equal to -1 and an in degree of child equal to 0, that child is not the root node, not -1 1. So q dot push child, we don't include 1 here. That's it. So with 2 will with all the 0 in degree ones, we will try to reduce the, because they are just going to add up the score, which because through those nodes we won't be able to reach the n, like from 1 to n they are not going to help in anything. That's why they are just going to increase the, like they are going to give the false increased value. So this is a bit of complicated question if you are haven't done questions regarding topological sorting. So we'll submit this in game routes. Okay, this goes now investigation. So this is a very easy question. This will give you a bit good idea about how the BFS works. So what we want to do, we want to travel from plane from one place to another, simply 1 to n, find the minimum price of such a route, basic Dijkstra, basic DFS Dijkstra, whatever. Minimum price routes are there. So whenever we get a minimum price, we simply add up the routes if it's already there, otherwise not. What is the minimum number of flights? We simply add them up. Maximum number of flights, we also add them up. Okay, so let's begin this question. Like, we'll understand this question as we code. So let's start. Basically, I think when we have to add or subtract, there is always going to be constant. Yeah, here's a modulo. Constant in mod is equal to 1e9 plus 7. And constant int infinity also. I think we should take 1e17, not 18. Like int n m. Okay. Scene n m. And then we'll have a vector of pair of int comma int. Adjacent list of n plus 1. Right. And we'll also have a vector of int of price n plus 1. Initially, let's say it's infinity. We're trying to minimize it. Then we have routes, minimum routes and maximum routes. Yes. Minimum routes, maximum routes. Okay, so initially price is going to be infinity, right? Price is like distance, we can say. And what? And routes are simply going to how many minimum price routes are there, and maximum number of flights and minimum number of flights in a minimum price route. That's it. And then we take an input for int I is equal to 0, a comma b comma w. I is less than m, I plus plus. Basically scene a, scene b, scene w, right? Adjacent list of a dot pushback what? We push back b comma w. Okay, so then we'll have a Dijkstra here, which will take care of our answer. And then we have to just print everything of nth value. Dijkstra. What do we have to pass here? I think we have to pass everything as list, price, routes, mi, mx, everything by reference, and update it along the path. And then simply see out price of n. What's the order here? Price, okay, this is the order. Routes of n, mi of n, mx of n, and l. Okay, so void Dijkstra. Generally, the question was in Dijkstra. First, I'll do this, then I'll do. So in Dijkstra, generally, we have to have cases na, if the price is you can say greater than or equal to, right? Like we used to have the condition if the price is like greater than or equal to or something. Continue. But here we are going to have three conditions. If the new cost is equal to that price, or if the new cost is less than that price, right? Okay, when we'll write the algorithm, then it will be easier to understand. So simply we'll have a priority queue, pair of int comma int, vector of pair of int comma int, greater of pair of int comma int, right? PQ. Now what we'll do, like basically push, what's the cost? 0 for the node 1. And then prices of 1 is going to be how much? 0, as we are starting from 1. And routes are also going to be 1, right? Like this is a route, this is the answer. And what? Initially we are here. Now what we'll do, we have to run basic Dijkstra. What we do in Dijkstra, while PQ dot empty. See, understand very carefully all the conditions. This is basic PQ dot top dot second, right? And int cost is equal to PQ dot top dot first, and then what you do, PQ dot pop. First we have that basic optimization, right? What was the optimization? If current cost is greater than the price of the node, we are simply going to continue as we have a better priority queue makes sure that we have a better values at the top, and we already got a better value, so we don't have to take care of it. But what if, not what if else what you are going to do, for auto child we'll go through all the children, right? You got a better value. From that node we'll try to decrease distance of all the children. Now if v is equal to how much, child dot first, and d is equal to what, let's say c is equal to child dot second. It's not child, it's child, I think. Okay, so v is equal to child dot first and c is equal to child dot second. Now there are three conditions. If the cost of this node plus the distance between this child and this node is greater than the price of the child, right? Simply what we are going to do, continue, right? Sorry, it's going to be v. Else if it's equal, means we found another route to this location with the same place, same price, else obviously it's greater. So if in case if the price is equal, what we do, we simply add the routes of child plus equal to routes of node. Okay, sorry. Also obviously we are going to do mod routes of child mod equal to, yeah. But in that case we found even a better even say distance. Simply routes of child equal to what, routes of node. We don't add it because we have formed new routes, new minimum routes. It's not child, it's v, I think. So yes, now we have found the routes, right? What about the price? Initial price is going to be same, but price here is going to get changed. Is equal to how much? Cost plus c. So with this we found the routes and the price. Now what you have to find, the minimum number of flights in a minimum price route. Simply, what is going to be the minimum number of flights of a child is equal to minimum of how much? A minimum of the parent node plus 1, comma, minimum of this. Similarly, maximum of this is equal to how much? Maximum of mx of node plus 1, comma, mx of v. That's it. Because there might be a possibility that that particular minimum value route is reached by some other index. So like we have like the minimum number of flights in a minimum price route. You understand now? For the same minimum price we can have many different routes, but if we get a new price, so simply is equal to how much? Mi of node plus 1, mx of v is equal to mx of node that's it. S, and also we are going to push pq dot push price of that v in the priority queue. I think that's it. Hopefully that's it. Let's try to submit this now. It's a very good question. I think with this question, our basic stuff, basic everything is completed now. Okay, so generally I'll be doing the binary lifting and other stuff in the part 2, where I'll also explain the like theory behind it, like because they are like actually difficult, but I'll still at least do like one question to get so you people can get a hang of it. Planet queries 1. This is a basic question. So you're playing a game consisting of n planets, and each planet has a teleporter to another planet, or the planet itself. We have to process k queries of the form. When you begin a planet on this, travel through k teleporters, which planet will you reach? Simply, we have to use binary lifting, or you can say a sparse table. Just basic binary lifting. Yeah. Okay. Basic binary lifting. Lifting for successors. Planets are numbered from 1 to n, right? Okay, planets from 1 to n, right? In sparse tree, will create a sparse tree of x comma k, where which will store 2 raised power kth successor of node x. That's it. This is just a befriend will store up to how much? Up to around 2 raised power 30 parents. Okay, so simply what we are doing, let's say from first we can go to the 4th teleporter. From 4th we can go to the 6th. From 6th we can go to some other value. So first parent of 4, first successor of 4th one will be 4. Second successor will be 6. Like that. We'll just store all those values. So this is just basic binary lifting question. Constant and mxn, how much? 2e5 plus 1. As we won't be needing to store more than 30 parents, right? Like 2 raised power 30, not 30, 2 raised power 30, I think. Yeah. Like we'll be storing the first parent, second parent, everything like that. So this basically, what is the input? N and q, number of planets and queries, and vector in t. So we'll just simply take in the input. Okay, now I'm actually starting to slow down a bit. Like I haven't slept in like lot of time. So basically simply we are going to see out dp of I comma 0. This is the first parents which you are storing here, right? First successors. And then we will fill the sparse table. Like if you just study about the sparse table, it's a very easy question. For int I is equal to 1, I is less than 30, I plus plus, right? For int node is equal to 1, node is less than equal to n, node plus plus. Simply first we are going to fill first parent of 2 raised power 1th parent of each one of them, then 2 raised power second parent of each one of them, up to 2 raised power 30th parent. So dp of node, how much, right, is equal to dp of node I minus 1, and also leaving this value I minus 1. That's it. I think I wrote something wrong. Yeah, there's going to be one more bracket. So the I minus 1th parent, for that we'll check what is its I minus 1th parent. Means for a particular node, we'll see what is the dp of whatever value is I minus 1th successor, right? What how we can say, we are trying to fail now. So example wise, dp of node of 2 means 2 raised power second parent is equal to what? dp of node of 1, whatever is its first parent, we'll see what is its first parent, 2 raised power 1th parent, means fourth parent of this is equal to whatever node we get as the second parent or successor, its second parent. So this is regarding the filling up of the sparse table, while q minus minus int a b c in a c in b, see out what, find successor of a comma b and l, and then we have to just implement the successor function. That is very easy. Find successor int node int k. Okay. So basically int s is equal to node, what we do, we for int I is equal to 0, I is less than 30, we try to find all the parents. Means if you have to find the 7th parent, right, so we divide it into 1 1 and 1, right? Means 1 and 1 in the sense fourth parent plus second parent plus 1th parent. So that's it. We are going through bitwise. If k and what, 1 ampersand I true, so s is equal to what, dp of s comma I, ith node, yeah, that's it, and then we'll return s. Just try to submit it. Planet queries 2, we'll be doing it later in the part 2 of the video, where we'll be doing the advanced algorithms. I think it, okay, there's a TLE here. Okay, it's not printing for some reason. What could be the reason? I don't know what's the reason. So we took an input 1 up to n. I think I know the reason. The reason is that condition iOS underscore base sync with std. I think it was scene tie something, false. I think scene dot tie false. I think it's null. And then again cout dot tie, it's also null. Yeah. Now let's try to submit. I think because of that IO stream for getting an input, it was giving error. So let's start with submit this. Okay, so we'll skipping planet queries for now. Okay, how many problems are still left in this? Well, okay, planet queries. Road preparation is regarding what? It's DSU. We'll do this one. Flights route check. The cities and flight. Your task is if you can travel from one city to another city. I think this is. I think so. These two are like Kosaraju's algorithm, like strongly connected components. We'll do these two and the DSO ones, right? And then we'll do the Hamiltonian path, yes, and night store. And after the 6 questions, rest we'll do in the part 2 of this. Yes. Okay, so I'll be back in a minute. I have to get fresh a bit. Okay, so in this question, road preparation, we are given there are n cities and m roads between them. The condition is poor that they cannot be used. So your task is to repair some of the roads so that there will be a decent route between any two cities. So in a way, we just have to find the minimum spanning tree, right? We have to print one. However, if there are no solutions, we have to print impossible. Okay, so we have to try to find a minimum spanning tree. Like if they are impossible is when like generally for a minimum spanning tree, we need to have at least n-1 edges to connect n nodes, right? So if they are not n-1 edges, so like it's going to be impossible. Yeah. So let's start this in road preparation. Yeah. So let's have a struct edge int sew constant int max n is equal to 2e5 plus 1, and then we are going to have vector of edges, vector of int of parent mxn comma minus 1. Yeah. So we have to just form a MST, and like for that we have to make sure that we have at least n-1 edges to connect n nodes. To connect n nodes. So this is just the basic stuff. Now before we start, we have to know a bit about DSU. DSU is nothing, it's just data structure where what we do, like if we have two nodes, we are given A and B, we'll find who is the parent of A and B. If like parent of the component of A comma B, if they have the same parent, then no problem, right? But if they have different parents, we are going to merge them, right? So how we do this? In find of A. So what it does, it finds the parent of A. If parent of A is not equal to -1, if parent of A equal to -1, which means it's a single node, so it is going to be itself parent, else we are going to return parent of A is equal to how much? Find parent of A. So using parent of A, we are going to keep finding parent of A till we reach a node which is like the topmost parent, which is only having itself as a parent, like that, something like that. And then we are going to have a merge function. What it's going to do, it's going to take int A and B. First we are going to find parents of A comma B. After finding parents of A comma B, if they are same, then no issue, we don't merge them. Else what we do, let's say parent of A equal to B, and then we simply return true. This is just basic DSU, this much only. Now currently what we have to do, scene M answer comma count, answer equal to 0, count is also equal to 0, right? We have to, yes, edges dot resize, otherwise it will give TLA again. Resize how much? 2m, yes. And then for auto, instead of auto we can also do this, I think. So I plus plus scene edges of I dot s, edges of I dot e, edges of I dot w, right? So after taking in the edges, like this is just the basic MST procedure. We just sort all the edges in the ascending order, of course, in the ascending order of what? Their weights. So use a lambda operator here, edge A, edge B, and then return A dot W less than B dot W, right? Oh, I missed a semicolon. And then what we'll do, we'll go through all these edges, in the edges, right? If the merge function for what, E dot S comma E dot E is returning true, then what we are going to answer plus equal to E dot W comma count plus plus. That's it. Like in if count is equal to n, right, n minus n, sorry, then we are going to simply see out what, answer and L, else we are going to see out impossible, backslash n. And a comma. So this is like a basic implementation of DSU, a very simple question indeed. We'll submit it now. Road preparation. Okay, so I think it will get submitted. Okay. Now similarly, there is road construction. A new component, this, and the size of the largest component. I think it's the same. We just want to find the number of okay. Initially we are just doing randomly parent of A equal to parent of B. The only difference we'll be having now is we'll do it by either there are two techniques, I think, like compression by rank or size, DSU by rank or size, and path compression. Yes, DSU by rank and size and path compression. Write int find, int node, right? And let's say instead of making it global, let's pass it for int of parent, ampersand parent, right? And then it will be if parent of node, like a full generic way of writing, is not equal to -1. Return, I think if it is equal to -1, yes. And that's the same thing, we can write it up and down, that doesn't even matter. Return if it's else return parent of node is equal to what, parent of find parent of node comma parent. Now let's write the merge function also. I think we have to pass int A and B, and then we have to also pass the rank here. Yeah, or we can also do size, but I prefer the rank. No, it doesn't even matter at all. For int I parent, basically A is equal to what, find of A comma parent, B is equal to find of B comma parent, right? If rank of A is smaller than rank of B, so we are going to swap them, right? Because we want A to have the higher rank. So what we are going to do, parent of B is equal to A, that's it, and rank of A plus equal to rank of B. It's simply like adding all the rank of its subchildren, and then return rank of A. So this is just for that power thing, size of the largest component. Okay, so like this, what we do, int n m scene n m, what we have to find the number of component and the size of the largest component. Okay, so mx is equal to 1, right? Vector int of rank is going to be n plus 1 comma 1, initially everyone is of one size and its parent is -1, that is it's itself. Then simply you have to run out of a, b, I less than m, I plus plus. Now we'll take in elements c in a, c in b. After taking, we will check if they have the same parent or not. If find of a comma parent is not equal to find of b comma parent, like that is they have different parents, so I'll try to merge them. Maximum what? Mx comma merge a comma b comma rank comma what? Parent. Yeah. And then we'll simply decrement n minus minus, because like two of them joined. Yeah, that's it. Then we have to do, okay, so after each day we have to find the number of components, right? So we have to just see out n and then a space and then mx and then so this is just basic DSU. After each day we try to merge, decrement the number of total components, print out the maximum size. That's it. So with this, road construction is also done. Then we have flights routes check. The n cities m flight connection. You're tasked to if you can travel from any city to another city. See, we can travel from any city to another city if there's only one strongly connected component, right? Now for that, what is the procedure of flights routes check? For a strongly connected component, what is the general procedure? Like we have how to do this. Strongly connected component 1. Okay, I'll tell this a bit in detail. What is a strongly connected component? Where each node can visit all the vertices in that strongly connected component. Now there are 4 strongly connected components. Okay, generally if we start a DFS from any one node in 1, it is going to reach all those 4, right? That's the issue. So what we want to do is we want to reverse the edges, right? We reverse the edges, but what will happen now if we do the DFS, that node would only do traversal in a strongly connected component. So we just have to find which node is it, like which node is the node with the highest finishing time, right? That's it. After we get that node, we just start DFS from it. Then it will complete the whole first connected component. Then we go to another node with like less finishing time but more than others, so it will complete it like that. So generally we have to do first 2 DFS. One is for finding the topological order, and then another DFS to like find the strongly connected components. Okay, so let's start this. Okay, constant int n is equal to 1a5 plus 1. I don't think we need this. Let's leave it for now. Just start with global everything. Int n comma m, c in n, m, number of edges in this. I think we'll make everything here. We need to have a visited, right? We need to have you can say a color determining which strongly connected it is belonging to an adjacency list, and after reversing the graph, a reverse adjacency list and the topological order. Okay, so int visited of n plus 1, column of n plus 1. You have to memsum that to 0, memset visited. Like we can also use vector with initialization. Okay, so visit list of m+1. So this is going to be adjacency list, this is going to be a reverse adjacency list, and then we'll have a vector of, just study about this. This is a very simple algorithm, topological order. We can also use tag for it, that doesn't actually matter. So like for int I is equal to 0, first we'll make the graph. Okay, scene A, B, adjacency list of A dot pushback B, and reverse adjacency list of B dot pushback A, right? For int I is equal to 1, I less than equal to 1, I plus plus. If not equal to what? Visited of I, we are going to DFS it. What DFS is going to do, it's going to find us the topological sorting, topological order, right? We don't have to pass the color because currently we are just forming the topological sort. So okay, we'll have void DFS1. Let's call it DFS1. Here what we have to pass, int node, vector, int of adjacency list, int visited, vector, int of topological order, right? So basically what we do, we visit a node, when we come back from recursion, we put it in the order. No matter where we start the recursion, we always will get the topological sort. Yeah. If it's not visited, DFS1 of child adjacent list visited topological order. Topological order dot pushback node. So with this we got a topological order passed by reference, right? Now we have the topological order, we have to reverse the order also. Currently it's reverse topological order dot begin, topological order dot end. Okay, so now we have to do another DFS, right? So we have to make the visited array 0 again. Now what we have to do? Initially we just simple basic DFS, and count is equal to how much? 0. I think we already had a count variable. Okay, we don't have. In count should be 1 or 0. Obviously there is going to be 1 as an answer. So let's have it 1 for now. In count equal to 1. We will have a vector int for answer. For auto what? IT in topological order, right? For auto IT in the topological order, we are going to do DFS2. If it's not visited, we are going to push back in, obviously, because we need to find the we need to find the two cities from which we cannot travel. So simply we'll pass it so that for each strongly connected component we have a city. Then we'll have DFS2, let's say. Or need to pass the current node, the reverse adjacency list, that's very important. You have to pass visited, color, because we'll mark which node. We don't have to pass the topological sorting, and we also have to pass the count, right? And then we are going to increment the count. Also, like in reverse graph, source will become sink. Yes. Auto this, if not visited, this. Now if count is equal to how much? 2, which means there is only one strongly connected component, right? Else see out no, and we'll do what? We have to print what? 2 cities, okay, from which you cannot travel to one another. Simply see out answer of 0, answer of 1, and that's it. Now we have to write the DFS2. This is also going to be a simple DFS. DFS2 in node vector into adjacency. Acha, we have to pass the reverse. Here it doesn't matter. I think int color, int cc. Visit of node is equal to 1. We visited that node, right? Color of node is equal to what? C. Like it belongs to that particular component. And then for basically for auto, child in reverse adjacency list of that node. If it's not visited, DFS2 of child reverse adjacency list visited color cc. Okay, so I think that's it. So with this, flight route checks is done. So like basically we have to do first do a DFS to find the topological sort. Then in that sort we do DFS in the reverse adjacency list and just increment as many, you can say, connected components there are. Flights route check. Okay, there are some wrong answers. Okay, huh? How is this wrong answer? Okay, this is like very stupidity, but anyhow. Okay, let's go to next question. There are n planets connected by m teleporters. 2 planets A and B belong to the same kingdom. When there is a route from A to B, your task is determined for each planet its kingdom, right? So I think it's the same mostly. First I'll just copy all this code in the other one, right? Okay, so this is copied. Just the thing is we have to, for each A and B, okay, we just have to print which connected component it belongs to, right? Yeah, that's it. So we'll just, I think, remove this part, right? We have to see out what? Print number of kingdoms, count -1, not minus, count -1, and then we have to just print out what? The color which you're storing earlier. See out color of I. Yeah, I think this will suffice. Planets and kingdoms. Yeah. Yep. Okay, these questions we'll do later. Like some are Euler path and other stuff, we'll be doing them later on. and then we'll just finish this stream. You can say it has already been above 4 hours. We'll finish it with these two questions: Hamiltonian flights and night store. Hamiltonian flights. This is just a very basic, not basic, a very famous question. Like we just use DP with bit masking to store all the paths which we can do, right? So there's only one thing in this question. Like what we have to do is to how many routes are possible from going from 1 to n, right? The first line has two integers, number of cities. The cities are numbered from 1 to n. City 1 is this, city n is this, right? So what we are going to do, constant int mod is equal to 1e9 plus 7, constant int mxn which is equal to how much? 21, right? Like maximum cities are 20, right? And now what we are going to do, generally it's very easy. Like we have to just calculate the number of paths, but the problem is if we go from a node to node A to B, there is an edge from B to A also. We can't use it back, like otherwise it will be like infinite number of paths. So we have to just visit each city once. So what we'll do, we'll use a bit mask to keep track of it, and we can also use a visited array though. But when we then we have to loop our visited array for every node. Okay, so if we go from A to B, right, a node from A to B, and there is a edge from B to A, we can't use it to go back, right? So we have to visit each city exactly once, right? So we have to use a bit mask to keep track of it. Okay, that's it. Okay, we have to keep track of it. Now what we'll do, we can do it with both approaches. Like first I'll start with one approach, then I'll do with another approach. The difference between the approaches will be that first we'll be having a set bit to keep track of it. Other time we'll be having an empty integer like to keep track of it. That's it. So let's start. First, basically what we are going to have, int n and m, number of nodes and number of edges, right? So we'll have a vector int of adjacency list, right? And then we'll have a dp of 1, like we'll use the set bits in an integer to store, to see like which have already been visited or not, right? So how we do this, int n m, basically first we'll form the graph. I is less than what m I plus plus int x we're going to keep it 0 based indexing. Yeah. Mem set of what? dp of -1, size of dp. Yeah. And then we are going to see out what? DFS. Here we are going to consider all set bits as indicating that we have not yet visited that node. That's it. And let's make the DFS int DFS. We have to pass the mask and the node. Now what we'll do, see, when we reach a node, right, first we are going to unmask a bit. Which bit we are going to unmask? How we are going to unmask? XOR equal to 1 this node. I think this is the right way, right? So we unmask that bit, like if it is set, it is not going to be unset anymore. Now, if mask is equal to 0, right? See, their directory edges, it's such that we will reach from 1 to n always, right? So if mask is equal to 0, if mask equal to 0, right, we are simply going to return 1. Obviously, basic condition, but obviously when mask will be 0, we will be at n minus 1, but there is a thing that we can reach n minus 1 node without the mask getting 0. Then simply we are going to return 0 to it. Another base case, if we have already been through that DP state, we are just going to store it, return it, return DP of mask node, and answer is equal to what? 0 for auto child and adjacency list of node. What we are going to do now? Basically we are going to see if that child is not yet visited, right? So if its child is not yet visited, then whatever answer we'll get from that child by setting that child, right, we are going to use that. So answer is equal to what? Answer, so we have to take mod also, right? So answer plus DFS of mask comma child hash mod, right? So it's done. Then we have to simply return what? DP of mask node as answer. So first we are unsetting the bit like we have used it. Then if we'll reach the mask equal to 0, obviously we have one answer because they are directed path, and obviously then we have reached n minus 1. Else, if a node equal to n minus 1, we return 0 if we have already visited the DP state. So this is like basic DP with bit, not DP with bit mask, just like basic. Yeah, okay. So now what we if we have to change it a bit, right? How we change it? So let's create another DFS, right? Int DFS. Let's remove all this code, right? We'll change everything. Yes. Let's comment everything out, right? So earlier we used the set bit approach. Now we are going to use the unset bit approach. Okay. So int nmm, right? We'll have a DP as earlier 21 1 21, right? We can also use max, and it doesn't even matter that much. Vector int of adjacency list of 21, right? We'll have a solve function or a DFS, whatever you can say. So what we are doing, I think this much it should be same. I'll just, okay, this much is just going to be same. Okay, cout DFS 2. Here we are going to pass what? Instead of 1 raised power n, we are going to pass 1 raised power 0, comma 0, and then see. Also, why we do this minus minus? Because 1 raised power x is equal to x plus 1 bit. So we make sure to keep it in the constraint. Now let's write the DFS2 int DFS2 int mask int node. Basically instead of that, now what we do, we have to check So we have a built-in function for it. Built-in, I think pop count, yeah, it's built-in pop count of that particular mask is equal to n. We are going to return 1. But if we reach node at same as condition before the mask is complete, then we are going to return 0. Similar like dp of node of mask is not equal to -1, we are going to return dp of node of mask. Okay, so okay, now the rest is going to be the same as above also. Int answer is equal to 0 for auto child in adjacent list of this node. If mask, we want to see if this bit is already set, we are simply going to continue. Else we are going to answer is equal to answer plus bfs2 of child, and then we are going to set that bit here, like by doing OR with that particular value, and then simply mod, and then we are going to return dp of node mask is equal to answer. So with this, both of the approaches are with this we have completed both the approaches of this question. Okay. Okay, I'll try to submit this, and then we will move on to the last. Okay, the runtime error. Nice. Why is there a runtime error? Okay, if we got answer with one approach, so we should also get with another. I'll just see what's the error. For int I equal to 0, sin xi, we're pushing back correctly. dp -1, dfs2. Okay, this is the error. We have written the order of DFS wrong. Yep. Now it will get submitted. There's so many questions now. It's even like which one to submit. Yep. Then we'll move on to the last questions. How many we have completed till now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. Then I think 5, 4. So 11 questions will be left. We'll do those in part 2, as they are going to be comparatively difficult than these. We just have one more question left. With this we'll just complete our stream. I guess 4 hours 30 minutes. Now what's this question here? Knight store. So we are given a starting position of a knight. See, I haven't actually done this question, so I have no idea. So we are given a starting position of a knight. Your task is to find a sequence of moves so that it visits every square exactly once. Okay. So we just have to like basic DFS. For a knight, there are 8 moves. It can move to 8 directions. So we have to find a sequence of moves. Yes, so there can be infinite sequence of moves. We can do one optimization such that we'll go to a move where like maximum possibilities are there. That's it for this question. What is x and y is going to be the input. So let's start. So int dx array, it will store what? The dx values. So it will be -2, -2, -1, -1, 1, 1, 2, 2, and then -1, 1, -2, 2, -2, 2, 1, -1, 1. Yeah, we'll have a board, just 8 cross 8 as it's chessboard, right? So what is this question actually? This is a basic backtracking question where we have to find one solution, right? So what we can do, optimization here, optimization, that we will choose the next square such that it has maximum number of squares to go from it. That's it. Otherwise we might get TLE. It doesn't even matter that much, right? So we'll have a basic boundary function, as there are no like walls here. Int x, int y, return x is greater than or equal to 0, and then x is less than 8, and then y is greater than or equal to 0, and then y is less than 8. That's it. And then we are going to take an input, int x comma y, c in x comma y, right? I think we'll make it 0 based indexing, as board is from 0 to 7. That doesn't matter actually, so we'll like also memset the board to 0, because this also gives TLE sometimes in CSES. We have to memset all the values. So we'll just run a DFS. Bool answer is equal to what? X comma y, like initial coordinates and the first step, and then we are simply print for auto ampersand r in board, for auto ampersand c in r. We have to see out column, right? C, and then after this we have to see out handle. We have to see out handle. We have to see out handle. So that's it. Now we'll make a DFS function for it. Yeah, I think we need, yeah, that's it. After this it's going to get completed. Bool DFS int x, int y, and the current number of move, right? So currently board of x comma y equal to move. Like if we get to this move node, then we put it with the move. It's like using a priority queue type. And what's the base condition? We have reached all the, we have used all the moves. Return true. Right, now we'll have a vector of int for answer, and then what we'll go through all the 8 steps from a particular node, right? Okay, so int nx is equal to x plus dx of I, int ny is equal to y plus dy of I, right? Now if it is valid, if this position is valid, nx comma ny, and then it has not already been visited, board of x comma y equal to 0, then what we are going to do, we are going to v dot pushback answer dot pushback. In answer what we are going to push, like let's say some value, and nx comma ny. What's the value going to be? We'll get it through another function, right? Let's say int d is equal to, we'll create a value function, like which move has the maximum value. Now, after this, what we are going to do? After this loop is completed, we are going to sort v dot begin, right, and v dot end, right, on the basis of what our value is. We have to, I think, after sorting on the basis of the value, we have to run what? We want to have the minimum number of nodes or the maximum number of nodes. I actually don't know. Okay? I think we should have as many nodes as possible from that node. So it should be greater of int. Then for auto, all the moves, where if DFS of IT of 1, comma IT of 2, right? Move plus 1. Okay. Simply we are going to return true. And then we are again going to mark the board as unvisited like we do in basic track backing. So we mark the node and then we mark the value, then we found the solution, then we track back. So I think answer should be value. Now what should be the value function, right? Int value for a node int x comma y is int value which is equal to 0, right? For int I is equal to 0, I is less than 8, I plus plus. If is valid x plus dx of I comma y plus dy of I value plus plus return value. So basically what we are calculating the maximum number of nodes we can reach from it. Maximum or minimum? I think it should be maximum, yeah. I think it should work. Hopefully it should work. And it should be minus how is their compiler? I'm actually very tired, though. Let's see. There should be no error such as this, yeah. What nonsense. It's not unused. So, what kind of error is this? Hmm. So, array string is valid is also right. The lineage to x and y, the definition x and y. Uh, 1 minute. See the x and y here are x is second column, first row. What I am taking in input x and y also. Board x coordinate is how is that compilation error? I don't know. Okay. Okay, this is wrong answer. So that actually doesn't matter. Like unused variable that doesn't any make. Okay, so greater in. Okay, so we have to sort on the basis of decreasing move. Na? So R begin, R end. Let's try this. Oh, oh. Okay, so that's not the issue. So basically, what we are doing int x and y. Basically, first we are going to take scene y, scene x, mem set board 0, bool answer DFS for ampersand row in board, for ampersand column in row. We are going to column is the value, right? See out and then nice. Int value. If it's valid position, okay, so I don't know what's wrong here now. I'm actually very tired. I don't have the energy to think now. So DFS we are doing right, right? If move equal to 64, return true. That's it. In the end, will return false. That doesn't actually matter. It's just for the inner, for getting the value. Okay. Okay, I'll just see. Give me a minute. Okay, so okay, we just had to put nx and ny here. Let's try to submit this now. Really? I think it should be, I don't know why, but it should not be in increasing order. It should be in decreasing order now. And I think with this we'll get our submission. Okay. But I still think it should be in increasing order. But anyhow, so we did around like 25 questions. I'll just give a overview of everything we have done till now. Like this is a very nice problem set. Like we'll be doing Euler path, two-side problem, uh, Fulkerson algorithm, max flow, everything in the part 2, and also more questions of binary lifting, other stuff. Now let's do a quick revision of what we did till now. So so basically first we started with the introduction, like basic traversal techniques, right? Then we went to the question counting rooms. Here we just connected the number of connected components will give us the number of rooms. Yeah, that's it. Simple question. We got to know about basic DFS. Labyrinth, we can also do it using DFS. It was just calculating, okay, where is it? Okay, so in this question, we just had to find the location. So here we did BFS, plus we also like got to know about this technique of track bagging and then printing of elements. Then this was building roads. This was basically storing the connected components. It was a very easy question. Then message routes. Okay. So what was this? Okay, this was just storing parents. Like this was a very basic question. Then we had like building teams. We had to, okay, this was to check for the bipartite graph. Okay, so this was just basic cycle detection. Yeah, this monsters one was very nice. It's like a very good implementation question. Not just implementation, it's like very good technique also. And then shortest routes one, I think. So this is from where the algorithm start, basic Dijkstra and stuff. Then we went to Floyd Warshall. Yes, Floyd Warshall algorithm. And after that we went to, I think, Bellman Ford algorithm. Like, yeah, no, we were doing we went to Bellman Ford. Then we did some questions on Dijkstra, like State Dijkstra. And then this is like advanced Bellman Ford, something like that, for negative cycles. Then we have flight routes. This is also Dijkstra, a bit different. State Dijkstra with different k states. Then we had a round trip too for like cycle detection in direct cycle detection in edges, I think. No, this was just normal question. Yeah. Then course schedule, basic topological sort implementation. Then we had longest flight route. Now this is what okay, this is like DP on trees. Yeah, what I'm thinking is after I complete the CSES graph and some other maybe like introductory problems or maybe mathematics, I will go with tree algorithms next. So like whole graph and tree is completed, like DP with trees and everything, and DP also. So longest flight route, if okay, so this one is also done. This was just basic DP, right? Game routes, it was regarding, yeah, this is a very nice question. I might not have explained very properly. So what was it actually like? Basically, we are doing this ways of child plus equal to this. This is basic PNC. We are just adding the ways in the child, adding ways of node to the child. But there is one issue. When we make the graph, we'll see that all nodes with in degree 0 are going to give additional answer. That's it. For investigation, this is a question. This is a very nice question. It's like Dijkstra, a very good version of Dijkstra. Then we had planet queries. I think planet query, it's like binary lifting, different type of binary lifting. Just we had, instead of direct, we had like teleporters to a particular index. Then we had DSU, two questions for DSU, very simple and crispy questions. That's it. Then we had Kosaraju algorithm. It's a very nice algorithm when you get to understand it properly. Yeah, like it takes some time to understand, but it's a very nice algorithm. Then 255, it was the same Kosaraju algorithm, strongly connected components. Then we did Hamiltonian path. This is just basic DP with bit mask, simple application. Then final question, night store. Yeah, like last question. Actually, the part two is going to be very difficult. Like for example, this planet queries too. So like it's going to take a lot of time to code that in a single video. So that's it. And this with this we have completed most of it. And I guess it's very late now, 5:17. So bye.